making a positive vibration and enthusiasm amongst all faculty members, research scholars, and participants of the program, this GIAN program. We also have Dean School of Physical Sciences, Professor H.S. Tiwari sir, University GIAN Coordinator, Professor M.C. Rao sir, Head of the Department, Professor K. Devangan sir, GIAN Course Coordinator, Professor G.K. Patra sir. A very good morning to one and all. I feel privileged to extend my warm welcome to all distinguished dignitaries, resource person, all dean present here, all head of the department, faculty members, research scholars, and participants on behalf of Department of Chemistry and on my own behalf. Now, as per the tradition and culture, it's time to take blessing of Almighty Goddess Ma Saraswati. Light and brightness is always equated with positivity, motivation. We welcome all dignitaries to join in traditional lighting of the auspicious lamp and offering flower to Ma Goddess Saraswati. May I invite all dignitaries, please? Thanks to Tarang Band for beautiful presentation of Saraswati Vandana. On this occasion, although our dynamic Honorable Vice Chancellor Sir is not present here, but his blessings is always with us. Atithi Devo Bhava. Welcoming our esteemed dignitaries is the moment of happiness for all of us. May I request Professor K. Devangan, sir, Head Department of Chemistry, to welcome our Honorable Vice Chancellor, sir, in charge, Professor Amit Saxena, sir, with a sapling. May I take opportunity to request Professor G.K. Patra, sir, Course Coordinator, to kindly welcome our guest of honor, Professor Raz Jelinek, sir, Vice President and Dean for Research and Development, Ben-Gurion University, Israel. Requesting Professor S.K. Singh, sir, S.K. Singh, sir, to kindly welcome Professor Vishwarup Chakravarti, sir, IIT Delhi. Requesting Professor Ashish Kumar Singh, sir, to welcome Professor H.S. Tiwari, sir, Dean, School of Physical Sciences. Requesting Professor Manorama, madam, to welcome Professor M.C. Rao, sir, University GIAN Coordinator. Requesting Dr. S.S. Thakur, sir, to welcome Professor K. Devangan, sir, Head Department of Chemistry. Requesting Aarti Srivastava, madam, to welcome Professor G.K. Patra, sir, Course Coordinator of this program. Thank you, madam. Moving ahead, first and foremost, I invite Professor K. Devangan, sir, Head Department of Chemistry, for his welcome speech for the August gathering. Sir, please.
Thank you, ma'am. First of all, good morning, everyone present here. So today, first, I would like to salutation Guru Ghasidas Baba and greeting to all of you. It is my great pleasure to extend a warm welcome on the behalf of organizing committee, GIAN courses, Environmental Technology. We are truly delighted to have such a distinguished gathering of guests, experts, professionals, scholars, and students assembly here today. Today our chief guest, Professor Honorable Vice Chancellor Sir and Vice Chancellor Madam, they are not present here, also Registrar Sir, but some word I would like to say about them. So here first, in their absence, I would like to welcome our Vice Chancellor, Sir, Guru Ghasidas Vishwavidyalaya, and also our Guru Mata, Madam, Professor Nilamri Dave. Due to their some other assignment work, they could not present here. Their encouragement, guidance, friendship, and positive approaches always encourage to organize this kind of the program and event in our university. In GIAN program, not only in our chemistry department, it was also organized biotechnology and some other university, and future it will be also. So there always that guidance regarding the science, technology, etc. always encourage our students, faculties, and staff also. In this welcome ceremony, I welcome our today's in charge, our Vice Chancellor Sir, Professor Amit Saxena Sir, and also Director of IQAC, cell. He is always with us whenever we need, when we contact with him to for any purpose, anything. So always he support us in giving, blessing us. Today he is with us, and he is acting as a today chief guest. So today I welcome Professor Saxena sir, and again in continuations, I heartily welcome our chief guest of honors and distinguished subject expert, Professor Raz Jelinek sir, Ben-Gurion University, Israel, and Professor Viswarup Chakravarti, Indian Institute of Technology, Delhi. Welcome, sir, again. Your valuable thoughts and experience will help us to understand the role of nanoscience and nanotechnology for the environment in greater impact. I hope our participants and teachers and research scholars will be benefited from your knowledgeable lecture in these sessions and coming sessions. So I also welcome our well-beloved Professor H.S. Tiwari sir, Dean, School of Physical Science. You have always been a source of inspiring for us. Your practical guidance, caring personality were highly influenced in making this event successfully. I also welcome Professor M.C. Rao sir, Vishwavidyalaya GIAN coordinator, for all his cooperation in organizing these courses. In this series of welcome, course coordinator Professor G.K. Patra and co-coordinator Dr. Neeraj Kumari, research respected delegates, teachers, officers, employees, students, research scholar, participants, media partner, you are most welcome in this ceremony. And also other department, Professor Murthy sir and Professor Tripathi sir present here, and Dr. Kiran Thakur and other men, they are present, they are coming from the other. So you are welcome in this welcome ceremony, sir, and this GIAN courses. We are fortunate enough to get support by the Ministry of Education India to materialize this event. So we thanks to Ministry of India for the supporting financial support. Finally, I would like to welcome all the guests, organizer and participant. Ministry of Education, whose presence and cooperation made this event possible. Let us all join hands to make this course not just an event, but a memorable experience that will leave a lasting impact. So thank you for being here. Jai Bharat. Thank you.
Thank you, sir. Thank you very much. To commence the proceeding of the day, may I take opportunity to invite Professor M.C. Rao, sir, University GIAN coordinator, for his valuable insights. Sir, please.
Thank you, ma'am. Honorable Vice Chancellor, in his absence, in charge Vice Chancellor, Professor Amit Kumar Saxena, the Director of IQAC also. Madam Nilambari Dabe and Registrar both were absent due to their personal and academic assignments. The Dean School of Physical Sciences, Professor Tiwari, Head of the Chemistry Department, Professor Devangan, our distinguished experts, Professor Raz Jelinek, Ben-Gurion University, Israel, Professor Viswarup Chakravarti, IIT Delhi, and senior colleagues, esteemed faculty members, dear participants and students. A very good morning to one and all. At the outset, I express my sincere gratitude to our Honorable Vice Chancellor, who was absent today due to his busy schedule, for his commitment and unwavering encouragement in strengthening academic excellence through international collaborations. Basically, the GIAN, it is a short form of Global Initiative of Academic Networks, is a visionary program launched by the Ministry of Education, Government of India, with an aim to bring an eminent academic experts, researchers, entrepreneurs into the Indian higher education system to facilitate the co-teaching of advanced courses to Indian students and fostering collaborative relations with experts from all over the world. This also serves as a platform to exchange of knowledge and ideas on a global scale. These programs offer a great opportunity for all of you to closely interact with on cutting edge areas with the eminent international experts for a considerable duration. Generally the course will be a 5 days or 10 days. I think this course is conducting for 5 days program. So this good amount of period you can continuously interact with the experts and you can take the benefit out of them. By participating in these programs, you will gain invaluable insights, practical knowledge, and international perspectives that enrich your academic pursuits and future careers. Therefore, I urge all the participants should actively engage with the sessions, interact meaningfully with our esteemed resource persons, and carry forward the spirit of inquiry and collaboration that defines academic excellence. Sir, all these lectures will also be live streaming on YouTube, and which is accessible not only for the present participant, it is also accessible throughout the India as well as throughout the globe. And also these lectures will be repository will be taken by the IIT Hyderabad, and in later stage also all these lectures will be available on YouTube. As and when you require, you can go through and access the lectures. For faculty members also, the GIAN creates an opportunity for possible collaborative research with international experts. I therefore, Professor Patra, requesting to arrange one interaction session with the faculty members of physics and chemistry so that they can explore some possibilities for future collaborations in research. With this, I would like to thank the National Coordinator, IIT Hyderabad, for sanctioned 5 courses under Phase 4. So far, we have completed 3 courses, and this is the 4th course, and we will be having one more course in the next month. That is again from the Biotechnology Department. I thank the course coordinator, Professor Patra, for giving me this opportunity. And now the faculty members of chemistry and physics, now the phase 5 is open. You can submit the proposals by end of the September. The 30th is the last date for submission of proposals. So I request the dean and the heads to encourage the faculty members to submit more and more number of proposals under phase 5. So thank you once again.
Thank you, sir. Thank you for your valuable insights. Moving ahead, may I take opportunity to invite Professor G.K. Patra, sir, course coordinator, for brief outline about the course.
Very good morning, one and all present in this hall. Chief guest of today's program, Honorable Vice Chancellor, Professor Alok Kumar Chakraval, sir. Due to his very busy schedule, he is not present with us. Today, with us, the officiating Vice Chancellor, Professor Amit Saxena, sir. We are also having with us the Chief Guest of Honor and Course Instructor, Professor Raz Jelinek, who is the Vice President and Dean of Research and Development, Ben-Gurion University, Negev, Israel. Another course instructor, Professor Vishwarup Chakraborty of Department of Chemistry, IIT Delhi. Dean School of Physical Science, Professor H.S. Tiwari, sir. Dean School of Mathematical and Computer Science, he is also with us, Professor Murthy, sir. And Chief Warden of our university, Professor Pradibha Mishra, is also with us. And we are also having Professor M.N. Tripathi, Senior Professor of Department of Physics, and all the dignitaries, Professor M.C. Rao, sir, who is the University GIAN Coordinator, our head, Professor K.C. Devangan, sir, all the other deans, heads of the departments, faculty members, dignitaries, participants, dear students, and my dear colleagues. Very first, I would like to thank our Honorable Vice Chancellor, sir, a visionary, inspiring leader, and an academic torchbearer, a compassionate administrator, the chief architect in transforming our institution towards excellence, inclusivity, and innovation, who has given us this opportunity to conduct this 5 days GIAN course on the most relevant topic, environmental nanotechnology. For his busy schedule, he is not with us, but his blessings are always with us. We are blessed to have with us Professor Amit Saxena, sir, whose radiating compassion, supportive nature, caring spirit, and versatile knowledge have always enlightened us. It's our proud privilege to have the chief course instructor, Professor Raz Jelinek, an expert of United Nations Sustainable Development Goal and climate change, co-editor of the Journal of Colloid and Interface Science, who has accepted our invitation and come a long way from Israel. Happy to share you, sir. Very recently, we have secured the 22 ranked in Sustainable Development Goal in the NRF ranking of India to 2025. We are grateful to Professor Chakraborty and Professor Binod, who will also deliver insightful lectures in this course. India is rapidly globalizing and has become the fourth largest economy in the world. But the rapid pace of development would have been possible by the expense of damage of the environment up to some extent. The major megacities of the country, including the nation's capital, New Delhi, regularly feature among the most polluted cities of the world. Environmental nanotechnology is the application of nanoscience and nanomaterial to address these environmental challenges like pollution, resource depletions, and sustainable development. In the coming 5 days deliberation, the course instructors will demonstrate how the principles of nanotechnology provide the solution of environmental pollution, energy, resource management, and sustainability through 12 modules and 5 tutorials. The modules are Introduction to Nanotechnology, Nanomaterials, Pollutants and Remediation, Green Nanomaterials and Agricultural Applications, Nanomaterials for Water-related Applications, Water Desalination, Remediation, Oil Spills Treatment, Bio-Nanomaterials and Environment, Nanotechnology and Climate Change, Energy-related Issues, Nanomaterial for Energy Storage, Batteries, Supercapacitors and Hybrid Systems, Nanotechnology for Environment, Sensor for Volatile Materials, Electrospun Nanofibers for Environmental Applications, Environmental Nanotechnology, Perceptions and Future Prospects, and also, as you mentioned, that question and answers and discussions are also there in our. Although the concept of nanotechnology is relatively modern, its fundamental principles were known from a long time in India for the centuries. The nanotechnology-based applications were extensively used, especially in the therapeutics and the Ayurvedic medicine. Ancient Indians and also the metallurgists, they exhibited their remarkable skill in producing the wood steel and rust-resistant iron pillars, indicating an understanding of nanostructured materials long before modern science recognized them. Similarly, the preparation of the herbal kajal, which contains the carbon nanoparticle, point out early knowledge of the nanomaterials in cosmetics. The use of the herbometallic formulation in bhasma, the application of the ultra-thin metallic coatings on the artifacts, and also the presence of the carbon nanoparticles in Ajanta paintings that provides the India's expertise in nanotechnology. I wish you all very fruitful learning experience on environmental nanotechnology and comfortable stay in our Laskin campus. Thank you so much.
Thank you, sir. Thank you for sharing the details of the program. Proceeding ahead, may I request Professor H.S. Tiwari, sir, Dean, School of Physical Sciences, to share his valuable words and blessings. Sir, please.
So I am thrilled and honored to have the opportunity to address at this significant gathering. We are especially honored to have with us today chief guest, Professor Amit Kumar Saxena, sir. He is also director of IQAC. Then guest of honor, Dr. Vishudip Chakraborty, IIT Delhi. Guest of honor, foreign faculty, Professor Raz Jelinek. And in front of me, various deans of the various schools, teaching faculties of chemistry and other departments, and delegates coming from various parts of the country. This workshop is a vital opportunity to share ideas, learn from diverse experiences, and build connections with scientific community. Over the next 5 years, 5 days actually, not years, over 5 days, we have an exciting lineup of thoughts, provoking lectures, discussions, and interaction, as Patra sir was telling. We encourage participants to actively participate, share their insight, and make the most of every networking opportunity. I would like to extend a big thanks to organizing committee, for their tireless effort and making this event a reality. We are also grateful to generous support from GIAN funding and sponsors of this program, whose contribution has been invaluable. I am confident that this workshop will be an inspiring and fruitful experience to everyone. Let us come together to learn, collaborate, and make this event a resounding success. Welcome you all once again. Thank you.
Thank you, sir. Thank you very much for sharing your experience and vision. May I request Professor Vishwaroop Chakravarti, IIT Delhi, for his insightful comments. Sir, please.
All right. Am I audible? Okay. Good afternoon, everyone, and good afternoon, all the respected delegates in the dais. And actually, this is my third visit to this university, and it is quite privileged to visit again and again to here. And first of all, I would like to thank Professor Patra, who is actually invited me earlier also for the two important international conferences. And this is a special invitation to me because this is not like a conference. It is a program, and it is dedicated to specially for the students, because conferences are different and this course is different. Conferences where many scientists visit and they present their work. But in this course, it is particularly to enhance some literature knowledge and some research knowledge or some detailed understanding about the course topic that Professor Jelinek and Professor Patra has designed, that will be beneficial for all the students. So the thing is that, I'll be also delivering two lectures here in this course. And as you know that this topic, environmental nanotechnology, why it is so important at this moment in India. So as we move on, we are moving on towards a more sustainable development and sustainable society. So I am sure that Professor Jelinek will give you very in-depth idea about this topic, because he is having a lot of experience. Because I am also fortunate that I have spent almost 3.5 years in Israel in the university where from Professor Jelinek is there, and during that time I have interacted with him once or twice because actually we are in the same department, and I know him that he is a very active researcher, and he has also very active, recently he is the vice president of that university. That proves that he is a very good, administrative efficiency is also there. Apart from that, he has many collaboration in industry, so which proves that the academic research needs to be connected to the industry for the sustainable development, because whatever we are doing in the laboratory, it is not limited there. Something has to be connected to the industry for the sustainable development for the society. So I am pretty sure he will give those insights, and he will share a lot of experience about this industry research and academic research. And this course or this program has been, that's why designed by the ministry, to show that we can bring the foreign delegates or foreign expert and share their knowledge or lot of years of experience to the students, so that we can boost the understanding, also boost the efficiency, or boost the expanding your knowledge beyond the textbook. That is also important for the students who are pursuing probably PhD, because most of the participating students are PhD and some of them probably are from MSc background. But the interesting part here is that those who are pursuing PhD, they are also limited to one or specific in a subject domain. But once we will interact with such a good academician, you will be understanding that how I know him since last 10 years, he has very wide knowledge. He is not limited to only one topic. So he will be taking all the different topics to you in terms of different courses. So I am pretty sure this course will be successful, and I must agree that this university and particularly this department with a great vision, because this GIAN course is something different, as I said, from the conference or any other thing. And it is particularly dedicated for the students. So I sincerely thank Professor Patra for bringing me here, and also all the other delegates who are present. And also I particularly encourage the students, please discuss with Professor Jelinek about whatever the queries you will be having, because this course is only for you. And with this, I think I end up my story, and I'll be seeing you in the course maybe in the afternoon. Thank you so much.
Thank you, sir. Thank you for your remarkable insights. May I take opportunity to invite Professor Raz Jelinek, sir, Vice President and Dean for Research and Development, Ben-Gurion University, Israel, to address the inaugural session.
Good morning, everyone. First, I'd like to thank Professor Patra, who initiated this course, and all the distinguished people that came here. This is actually the first time I'm in India. Today is the first day I'm in India in my life. So this is very special. This is a very special day for me. You know, India really is such an important place in many things in the world, but especially in science. So this is one very good reason why I'm very happy to be here. Another reason I'm very happy to be here is because throughout my career, as you said, I did many things, but the contribution of Indian postdocs and PhD students for my career has been tremendous. So I really thank you and thank India for helping my career. So I really feel that coming here, sharing my knowledge, having this course is one way for me to say thank you. I like to teach, so I really look forward for a nice course, nice dialogue with the students that are going to come to this course. Indeed, environmental nanotechnology is something very hot and very important to humanity in many aspects. That is going to be one of the messages that I hope to give you in my course. I'm going to talk more about it on the first lecture, just describing this course in general. But I really think that we, as scientists, as professors, also as management, I really feel that our duty is to pass the knowledge and to share the knowledge with the younger generation. So this is what I hope to do in the course here. Thank you again, and I look forward to an exciting week. Thank you.
Thank you, Bharatji. It's okay. Thank you. Good morning, everyone in the hall. First of all, I congratulate Professor Gautam Patra. जाने दीजिए, क्लास से बड़ा नहीं हो सकता. So congratulations to Professor Patra for initiating and then getting success in getting this project, this GIAN program. Professor Raz Jelinek, please excuse me if I don't spell correctly. Professor Biswarup Chakrabarti ji from IIT Delhi, our Dean, School of Physical Sciences, Professor H.S. Tiwari ji, Professor Patra, Professor M.C. Rao, local coordinator, Professor Devangan, the faculty, Professor Charu Madam, Professor Murthy, who has already conducted the GIAN program, Professor S.K. Singh ji, Marumra Madam, Professor Pratibha Mishra Madam, Santosh Singh Thakur, Nirja Madam, all faculty members who are from here, from the colleges, all the research faculty members, everyone who is present in this hall. So, the purpose of the GIAN program, as especially mentioned by Professor M.C. Rao, because he is the local coordinator, is very well taken up by this university. And we have a large number of courses which are already conducted in this university. Very recently, we have this GIAN program in the biotech department, and they got 2 GIAN projects. One already conducted and one is in the next month. So, let me tell, especially the external Professor Raj and Vishwaji, that the university logo has one recitation from the Ramcharitmanas, Gyan Pant Kurban Ke Dhara. So Gyan is taken very nicely from that Gyan, from university ka jo logo hai, Gyan Pant Kurban Ke Dhara. So this is the same Gyan, global initiative. So the best part of this project is, this program is that we have the very, very well-known expert academician. As I can see from the 8 to 12 September program, that there are more than 10 sessions by Professor Raj and a few by Professor Biswarup Chakrabarti. So you have the benefit, you have the privilege to get as much as knowledge, expertise from the experts. You can also, the department and the faculty can also think about launching a new project, new course in the school, or some 2-3 credit course also they can initiate in the schools. As rightly said by Professor M.C. Rao, this is a golden time, golden opportunity for all of you to interact with the external, take up your queries, because as I understand that it is not possible to digest all the sessions, all the lectures. We are also teachers, we are also students. So, but focus on at least 4 or 5 sessions where you can extend your curiosity and keep in touch with the experts now and later on also. Because this 5-day, 8 to 12 September program is okay, good enough in the physical mode. But you can interact with them even after the program is over. And that will be the real success of the GIAN proposal, because Government of India is spending a lot of money in arranging these kind of projects. So you should take the best benefit, the best use of this. So Professor Alok Kumar Chakrabalji, due to his some other engagements, important engagements, he could not make it to come here, because whatever is going on at the campus, because of his dynamism and leadership, visionary leadership. So this is all possible because of his, and let me tell you that we are also standing at a very good position in the NIRF ranking this year. So all these developments, all these good news are because of his hard work and dynamic leadership. Professor Alok Kumar Chakrabarti, we really miss him at this occasion. And I congratulate once again all the supportive staff, all the faculty members, that they are able to conduct the course, and I am sure that the course will be a grand success to all of them. And once again, I extend my personal and university level gratitude to Professor Raj and Professor Chakrabarti ji, who came all the way from such a distance and had planned to spend their valuable time here. Thank you very much.
Thank you, sir. Thank you for your very enriching message, and thank you for instilling lot of hope and confidence among the participants. Now, it is the time to honor and express our token of gratitude to our dignitaries as per our tradition. May I request Professor K. Devangan sir to present memento, shawl, Shrifal and Ramayan to our Honorable Vice Chancellor in charge, Professor Amit Saxena sir, as a token of gratitude. Requesting Professor G.K. Patra sir to felicitate our foreign expert, Professor Raz Jelinek sir, with a memento, shawl, Shrifal and Ramayan. रामायण रामायण है रामायण ही संस्कृत में है. I request Professor Charu Arora ma'am to present memento, shawl, Shrifal and Ramayan to our guest of honor, Professor Biswarup Chakrabarti, IIT, Delhi. Inviting Dr. Bhaskar Sharma sir to present memento, shawl, Shrifal and Ramayan to Dean, School of Physical Sciences, Professor H.S. Tiwari sir, as a token of gratitude. Requesting Dr. V.L. Sahu sir to present memento, shawl, Shrifal and Ramayan to Professor M.C. Rao sir, University GIAN Coordinator. Requesting Dr. Suryavan Singh sir to present memento, shawl, Shrifal and Ramayan to Professor K. Devangan sir, Head Department of Chemistry, as a token of gratitude. inviting Dr. U.P. Azad sir to present memento, shawl, Shrifal and Ramayan to Professor G.K. Patra sir, course coordinator of this program, as a token of gratitude, sir. Thank you, sir. Moving ahead, now it's time to propose formal vote of thanks. I invite Professor Charu Arora, Madam, for putting the vote of thanks.
A very good afternoon to all present on the dais and off the dais. The GIAN program on environmental nanotechnology, I have been given the opportunity to propose vote of thanks. I feel privileged and honored for this, and I express my heartfelt gratitude to Department of Chemistry head and Professor Patra for giving me this opportunity. First of all, I would like to express my heartfelt gratitude to our visionary and dynamic Vice Chancellor, Professor Alok Kumar Chakraval. He is a source of positive energy in the university, and as a result, our university is achieving new heights day by day in the field of education, research, and innovation. This program has been possible only because of his visionary guidance and cooperation. I would like to thank in charge Vice Chancellor and President of this inaugural session, Professor Amit Kumar Saxena, for his guidance and cooperation time to time. Sir, your presence have been given. Your presence is very inspiring for this program. I would like to thank our international and national resource persons and guest of honor of this program, Professor Raz Jelinek from Israel and Professor Vishwarup Chakravarti, who has come all the way from Israel and Delhi to enlighten us. So your knowledge and insight will be invaluable to us. On behalf of organizing committee, I would like to convey my deep regards and hearty thanks to our registrar, Professor A.S. Randive, finance officer, and university grant coordinator, Professor M.C. Rao. They helped us in obtaining necessary administrative approval for organizing the event in our campus, and they have supported in all possible manner to organize this program. I express my heartfelt thanks to Education Ministry for approval and financial support to organize this program. At this juncture, I would like to thank our Dean, Professor H.S. Tiwari, and faculty, HOD and faculty members of Physics Department, they for extending all help and support we received towards this program. Today, my words are not enough to express the gratitude to convener of the program, Professor G.K. Patra sir, co-convener Dr. Neeraj Kumari, and all program organizing committee members, including faculty, non-teaching staff, and all research scholars of Department of Chemistry for their hard work and commitment to make this program successful. I would like to thank our dynamic HOD, Professor Khemchand Devangan, for constant guidance and support to shape this program. Finally, I would like to express my heartfelt gratitude to all the participants for their dedication, curiosity, and enthusiastic involvement. Your active participation is the key to the success of this program. We are eagerly looking forward to this week of learning and collaboration. Let us join all together to use this opportunity to prepare ourselves to embrace new opportunities and challenges in the field of environmental nanotechnology. This knowledge will lead us towards brighter future. Thanks to one and all who have directly or indirectly involved in organizing this program. Thank you all.
Thank you, madam. Requesting all of you to please stand up for national anthem. All participants are requested to go at outside of the Rajat Jayanti Sabhagar for group photo with the dignitaries. And next technical session will start from 2 p.m.
So I hope you are graduate students, you are PhD or master students. Yes? Are there? Okay, so no undergraduates here? Okay, so good, because it is not very complicated. It is relatively basic, but you need some scientific knowledge in order to understand what I'm talking about. Okay? So what are the objectives of the course? What we want to do is to understand how nanotechnology, which is a big word, a very big topic, very hot topic, relevant to many, many scientific disciplines, from engineering to medicine to materials to environment, how nanotechnology is connected to environmental things. That's the main objective of this course. We will talk about how nanotechnology can help the environment. So we will talk about environmentally friendly and green nanotechnology-based materials and methods. We will also talk about the risks and the damage of nanotechnology to the environment. Because like everything, there is good and there is bad. And nanotechnology can be good, but it can be also bad. And some of the things that we need to do is how to solve the bad things that nanotechnology is doing to the environment. And what else we will do? Just give you some ideas about new possibilities, new research possibilities in nanotechnology. Maybe after this course, you'll go out and you'll do great research on nanotechnology, and you will save the world. Let's hope. Okay, let me tell you a little bit about myself and about my research, because I'm also doing nanotechnology in different aspects. Okay? If you want to learn more about what I do, you're welcome to go to this website. By the way, Professor Patra is here, nothing more? Yeah. If you want, I can give you all the presentations, and then you can give it to everybody. Okay, so anyway, you can go to this my web page and see everything about me. I work on many, many things, different things. You know, the good things about being a professor is that you can do whatever you want if they give you money for this, okay? So luckily for me, there are many projects that I work on because students came to me and told me they're interesting, and I succeeded in some cases to get money to do the research. So I have a good activity, pretty substantial activity on sensors, specifically sensors for gas materials. And actually, in the middle of the course, I'll tell you about some of our sensors that involve nanotechnology. A very significant part of my research involves very interesting nanomaterials called carbon dots. Carbon dots, we will talk about them a lot in a few lectures. And what we do with them, we make, among other things, sensors. And we also use them for various biological and chemical applications. I also work on batteries and supercapacitors, energy storage. You know, all these things about energy are very important in the world these days. Alternative energy, how to store energy. As you're going to see in this course, nanotechnology has big significance for this field. And we also work with nanotechnology in energy storage. And finally, we also work on biological systems. We work on proteins that are very interesting. They are called amyloid proteins. Have you heard of amyloid proteins? They are proteins that make aggregates. Have you heard about Alzheimer's disease? So in Alzheimer's disease, we have amyloids in our brain. We, in my lab, trying to understand what amyloids do. This is not nanotechnology. I will not talk about it in this course. Maybe the next course, maybe the next GIAN course. But this is also something very different. So as you see in my lab, various things from energy to biology, from materials to sensors. So that's what I do, and you're welcome to visit my site, my webpage. And if you have any questions or you have any ideas, please write to me. I'm always happy to explore new ideas and new directions. This is a long list. Professor Patra mentioned this. The course will have 11 lectures, maybe 12, we'll see, because I don't have a feeling how it's going to go. I'm going to talk for 50 minutes, and then I'll leave some time for questions if you have questions. We will also have sessions, some time in between. It's supposed to be for tutorial, but I can answer questions during these tutorials. And also something that I think is going to be very interesting, we would like you to present some research. I understand that you already selected people, so you can select projects or scientific papers and make presentations. I think it's going to be very good for you. So let's just go quickly on the subject that we're going to cover in this course. We will start today with introduction to nanotechnology, just to see why people are so excited about nanotechnology. What is so special about nanotechnology? This is going to be the topic of the first two lectures. The second topic will be the bad things about nanotechnology. As we're going to see, nanotechnology or nanomaterials in the environment can be very bad for our health. And we will discuss why. If we understand why they're bad, maybe we can stop them from being bad. And this is actually also what we're going to talk about in this lecture, how nanotechnology can help us overcome the bad things in the environment. The third topic will be green nanomaterials. As you're going to see, nanotechnology and nanomaterials in particular can really help agriculture in many aspects, both in controlling agricultural processes and biological processes, and also finding new solutions to agricultural problems, what's called the green revolution of nanotechnology. We're going to see how nanotechnology can help to grow better plants, better crops, how it helps agriculture. The fourth topic will be the relationship between nanotechnology and water. We're going to see that nanotechnology or nanomaterials can be bad in water, but there are many interesting, unique applications of nanotechnology in cleaning water and making water safe for drinking. We're going to describe some of these technologies. Some of them actually we developed in my lab, and I'll tell you about it. The fifth topic, we will go specifically to a subsection of nanotechnology called nanobiotechnology. This is nanotechnology as related to biological systems, and we're going to see how nanobiotechnology is related to the environment, how it's bad for the environment and good for the environment. In the sixth and seventh topic, we will talk about nanotechnology and energy. Because here, in the energy revolution, in solar cells, in batteries, in fuel cells, all this huge world of energy, nanotechnology have really a very important place. And we will discuss it in our topics. The first lecture on this one will be nanomaterials in solar cell technology, mostly. And then we're going to have a lecture about nanotechnology and energy storage. You know, it's not enough to get energy from the sun, for example. You have also to store it for certain applications. This is a huge field in India and in the world, and we will talk about it in this lecture. The eighth topic, we will introduce sensors, environmental sensors. We will see how nanotechnology can help us develop new and innovative sensors for many things. For air pollutions, for water pollutions, for viruses, for particles, for many things. And last, we're going to talk about the future. Is the future good? Is the future bad? There are obviously risks about nanotechnology, like everything in life, but there's also big opportunities. And what I hope that you're going to take from this course is that you, as students, can take the opportunities, grab the opportunities, and make real contributions to the subjects of nanotechnology and the environment. Okay, so that's the first lecture, the first part of the lecture. Let's go on to the second lecture. Or let's start actually the course, not the introduction. 1 minute, find it. Okay. The title of this lecture is Nanotechnology from Imagination to Reality. I think it's an excellent title for the subject, because nanotechnology in large part started from some dreams, for some crazy imagination of scientists 40 and 50 years ago. These scientists thought that we can do magic things with nanotechnologies, and surprisingly, some of the things really happen, as you're going to see in a minute. So actually, the first discussion, the first thoughts about nanotechnology happened in 1959. This guy, his name is Richard Feynman. Have you heard of him? He won the Nobel Prize twice. in physics. He's really one of the main scientists for quantum physics. And in 1959, he wrote this article that was really not scientific, just like a story. And in this article, he said this sentence, "There is plenty of room at the bottom." And what he meant is that if you go to the bottom of the dimension, to very, very small dimension, you can do incredible things. He didn't know yet, or he didn't say what you can do, but he really thought that in the tiny dimension, the dimensions of atoms and molecules, you can really build a new science. And this was the birth of nanotechnology. Actually, Feynman didn't use the term nanotechnology. This term only happened about 30 years later, as I'm going to show you in a minute. But for now, let's just understand what do we mean by nanotechnology. So nano is actually a measure, a unit. Nano, 1 nanometer is 1 times 10 to the minus 9th meter. 1 billionth of a meter, a very, very small dimension. So nanotechnology is the technology of very, very small dimension. For example, the smallest atom that we know, hydrogen atom, is 0.1 nanometer, 1 angstrom. So nanotechnology does not deal with atoms, it deals with larger entities, even not molecules, some aggregates of molecules. Okay? The human hair, for example, the size or the diameter of human hair is 10,000 nanometer or 10 microns. So the human hair also does not belong to nanotechnology. Nanotechnology is the technology or the science in between the hydrogen atom and the human hair. And if we look at the entire scale of dimensions of the world, okay, and we see that a human, it's a very large human, okay, 2 meter, very tall, 2 times 10 to the 9th nanometer. Okay, and if you go down, if we talk about cells about human cells, about 10 micron. Bacteria, 1 micron, so 1,000 nanometer. And then we go into the chemistry world. This is a colloid of gold, a ball with lots of gold atoms. Here, we start with the nanotechnology world. Gold is about 100 nanometer, proteins about 10 nanometer, small molecules 1 nanometer, and that's the end of the nanotechnology world. Atoms, very small, they don't belong to nanotechnology. So the term nanotechnology actually was invented in the 70s, okay, by a Japanese scientist. His name was Noro Taniguchi. In 1974, he invented the word nanotechnology. Back then, nobody knew what he was talking about. Technology in such a small dimension. In the 70s, when you talk about technology, you talked about building cars, building giant computers. That was technology. But he had the vision to say that one day we can do technology in the nanoscale. In the 80s, this person, this guy, he was actually not a scientist. His name was Eric Drexler. He wrote a book The name of the book was Molecular Nanotechnology. Back then, when people read the book, they thought he was a joker. They didn't believe, they thought he just went crazy. He had these ideas about making robots that going to be sizes of molecules. He had talked about nanowires in the size of few nanometers. Nobody took him seriously. But when we look now on the world of nanotechnology, and we're going to see many of the things that he said in his book are actually true. They actually happened. And of course, as time went by from the 80s until now, nanotechnology is everywhere. It's not only in scientific newspapers, it's not only in scientific lectures, but it's also in the newspapers. If you open newspapers, you're going to see nanotechnology in many, many references, in many articles for the general population. I think many people in the streets, even not students like you or scientists, they heard the term nanotechnology. Maybe they don't know exactly what it is, but they heard about it. So you can see these, just a sample of 3 totally random articles from newspapers about nanotechnology. Okay, so nanotechnology in crime, nanotechnology in electronics, and in other aspects. The truth of the matter is that nanotechnology is not something new. This thing, this cup, it's a very famous cup, is in one of the museums in Europe. It was found in a dig. It's an ancient Greek cup. And what the Greek did, even without knowing, they made this cup with the glass, and in the glass, through metallurgy, metal processing, they had some material that when they shine light from the inside, it changed color from white, yellow to red. And you know why? The reason why it changed color, it's called a Lycurgus cup, I think. The reason why it changed color from by light is because inside the glass, they had small nanoparticles, inorganic nanoparticles. And nanoparticles, when you shine light, certain nanoparticles, they can take the light and emit light in a different wavelength. It's called fluorescence. So they saw the phenomena. They did not know why. Today, we know that this is a nanomaterial inside this cup. So we have nanomaterial even 2,000 years ago. Now, why people are so interested in nanotechnology? Why they're so excited about nanotechnology? The interesting, the interesting thing, thank you. The interesting thing is that when you study nanotechnology, you find that there are new physical properties. Okay? And there's new physical phenomena when you go to the nanoscale. There's new materials that you can make using nanotechnology. There is new applications, practical applications in physics, in chemistry, in biology, in engineering. And also, when you apply nanotechnology, you can integrate between different technologies. This is the nice thing about nanotechnology, and this is why many scientists are jumping in the field and trying to do nanotechnology. For example, if we look at these materials here, okay, think about it. We have a copper coin. We have sugar. We have alcohol. We have oil and water. All these materials, they have special properties. For example, copper. What do we know about the coin of copper? What do we know about it? It's conductive. It conducts electricity. It conducts heat. But these properties are related to the fact that we have millions of atoms together. However, when you take copper in few atoms and you make nanoparticles of copper, the properties of the nanoparticles will be totally different than copper, than the copper coin. Sugar. Why sugar is sweet? Because we have millions of molecules in our mouth, going on our tongue, and then we feel sweetness. But if we take one molecule or two molecules, we will not feel sweetness. And if we take few molecules of sugar and we make some nanoparticle of sugar, it will not be sweet. It might be something totally different. This is the secret of nanotechnology. We take materials that we know about and they give you very different properties. So nanotechnology is also multidisciplinary. You can have chemists doing nanotechnology. You can have electrical engineers doing nanotechnology. You can have biologists doing nanotechnology. Everybody is doing nanotechnology. It's very multidisciplinary. Okay, so now that we know the basics of nanotechnology, why we're interested about it, let's talk about the early dreams of nanotechnology. Ideas and dreams. Some of these dreams came true and some not. All what you're going to see now, these are computer-generated images. Surprisingly, some of these things were made recently and are real. But for now, or 20 years ago, or 30 years ago, they were just dreams. For example, okay, one of the early dreams, actually from the book of Eric Drexler that I showed you before, is to make a gear, just like an engine of a car. But this gear is built from atoms. Each of these are atoms. So this entire gear, maybe 10 nanometer, maybe less. Remember, this is just a picture on the screen, not real yet. Pump. Can we make a pump from atoms? Can we build a nanoscale pump or a nano pump? This is actually something that people succeeded to do. Wheels and gears. Let's see if it's going to work for me here. Yes. Okay. Again, this is a computer movie, but maybe it can make true. A motor, okay? This is actually like a lawnmower, something that moves, a motor from molecule. And actually, if you see this thing, this is a tiny, tiny robot that actually moves. It's not a nano motor like this, But still, this is something that on the way in 2000 to be a nano motor. Nanowires. Actually, nanowires are some of the best inventions of nanotechnology. These pictures are actually real nanowires that were made in the lab. Now, these days, many people make nanowires for various applications. We're going to see them very soon. Nanotechnology has been applied in great extent to the biological and medical world. I mentioned nanobiotechnology, and now I'm going to show you some examples of nanobiotechnology, both dreams and real things. For example, this is an early picture. What you see here is red blood cells, and here you have a sort of a nanorobot, okay, that goes into your blood, picks maybe a cancer cell, maybe a bad blood cell, and takes it out of circulation. Remember, a dream, but maybe it can be realized. This is another dream. This is a neuron in our brain. What if we can create a little computer, laptop, iPad, that you can put on a neuron and trigger one neuron, or read what the electrical signal in one neuron. This is another dream, how we can take drugs and target them exactly to a specific location of a disease. Okay, 1 minute, let's see if this movie will work. No, it's not working. Okay. Nanotechnology now. So we saw some dreams, some visions, some ideas. Let's see what actually happened. And the things that I'm going to show you now are development from the past 20 or so years. The first thing is, if you want to do something in science, you have to know what you're doing. It's not enough to stand here and talk about things, show you beautiful pictures and say, I can do this, I can do that. But you have to prove. You have to be able to study what you're talking about. And what I'm going to show you now is maybe the most important tool of nanotechnology, which helps you to actually visualize nanomaterials. And this is called atomic force microscopy. What we see here is an optical microscope. You know why optical microscope is not good for nanotechnology? Anybody has an idea? Why you cannot look with an optical microscope, with a light microscope, on tiny, tiny nanomaterials? Any ideas? The answer is low resolution. You know, with optical microscope, you can see things, the smallest thing that you can see are maybe 10 microns, 10,000 nanometer. This is because of the light that goes to the microscope cannot resolve small nanoscale material. So optical microscope is not good for us. What is good for us is an instrument called atomic force microscope. Do you know what it is here? you're probably too young to use it. This used to be an instrument for listening to music. Gramophone, sort of. Phonograph, gramophone. You know how it works? It had, this was the record, and the record has heels going up and down, and here you had a needle. And the needle was going up and down, and each up and down gave you a different sound. That's how you could listen to music. Some people say that the music from this phonograph was better quality than what you have today on your cell phones. But I'm not sure. This is like an urban legend. But anyway, this was the way many years ago people listened to music. But the concept that we see here, this is exactly the concept of atomic force microscopy. Because what we have in atomic force microscopy is a very, very small needle that the tip of the needle is the size of single atoms. Now, when the needle goes on a surface, it goes up and down, and can tell you about atoms sitting on the surface. So it can help you see nanostructures. So let me show you some examples. Here, what we see are atoms sitting on a surface. These are real atoms. You can visualize atoms. What you do here, we can actually write with the atomic force microscope. This is the needle of the atomic force microscope. You can actually take atoms and move them from place to place. And you can actually write things. Here, this is called AFM nanolithography. With the AFM, with this needle, you can actually write stories. You can write the entire Bible on a tiny rice grain. Thank you. You can actually use the AFM to build new computers, because the tip of the AFM can give you the 0 and the 1, the binary system, which is the basic of all computers. And of course, you can do AFM, as we saw, for nanolithography. Okay, just writing books, writing whatever you want, making any picture you want in a nanoscale using AFM. So the reason I showed you AFM is just because it's an example of a very important technique that can help us understand what we do. If we don't have a way to understand what we do, we cannot make progress in the field and design new materials. This is only one technique, the AFM, one of the early techniques, but it's only one. There's other techniques that we can do, and we're going to just describe some of them right now. One of them is nanolithography. There is this lithography that you can print newspapers or books in large scale. Nanolithography can do the same thing in a nanoscale. Okay? For example, that's what you can do with nanolithography. You can use nanolithography to make small objects that you can then take and use in various devices. From the early days of nanotechnologies, the nice thing that people did is design and produce nanoparticles in different shapes and morphologies. This is here a summary of the various nanostructures that we can make in the lab. And why it is important that we have so many nanostructures. For example, we can have little spheres, we can have nanodiamonds, we can have nanotubes, we can have nanowires, etc., etc. Each of these nanostructures have different properties. Each of these nanostructures can be used for different applications. The fact that we can have so many different nanostructures is the reason why we can do so many diverse things with nanotechnology. Let me just show you some examples of nanostructures that we can use. For example, these are nanowires made from a protein. This protein is called kinesin. It's a protein that you can find in our cells, in our tissues, and we can make nanowires from kinesin. What we can do with these nanowires, I don't know. When people reported these nanowires, they also didn't know. But they said, hey, we can make nanowires from biological molecules, from proteins. As I'm going to show you in a minute, these nanowires can be actually used in electronics. You can take these nanowires and make them conductive, and then you can build electrical circuits using biological molecules. Drug delivery. Drug delivery these days use a lot of nanomaterials. For example, these nano capsules. Why doctors, medical doctors like nano capsules? Because you can take the capsules and you can put inside the capsules drugs. In nanomedicine, they are called cargo. So you can take this cargo, this molecular cargo, put it in the nanocapsule, and then you can swallow the nanocapsule and it will deliver the drugs to somewhere in your body. Again, beautiful application of nanotechnology to medicine. Here, I'm going to show you a very interesting nanocapsule built from individual protein molecules. Let me see. I hope. No. Oh, too bad. Maybe I'll show you this after the break. Okay. The world of biosensors and chemical sensors is a very broad world that we have applications of nanotechnology. For example, nanobiosensors. We can take nanocapsules that will contain small molecules that we call them biomarkers. And then using these small molecules, we can sense what's happening in different parts of our body. These are called nanobiosensors. I told you that we can use biological systems in electronics. This is an example of the use of biological molecules in nanoelectronics for sensing applications. What we have here is essentially a transistor. A transistor that goes between one electrode and two electrodes. This is a small wire. On the wire, we put small biological molecule. And when these biological molecules, these receptor molecules, will bind their biological target, the current in this nanowire will change, and we will have a signal. This is called a nano biosensor. We can have nano biosensors also in other configurations. For example, we can have an array, a pattern of tiny biosensors. When each of these receptors can recognize a certain molecule. For example, this is a cell that is sick, maybe a cancer cell. If this molecule, this receptor molecule recognizes the cell, we're going to have a signal. Now, this recognition can happen only because this molecule is very, very small. It's a nano biosensor. Actually, a practical application of this concept of nano biosensor, is called a DNA chip. This is actually a commercial product that is not so expensive. And what you can do, you can have an array of different receptors, different molecule, and by doing this sensing, you can know if somebody has a disease, maybe has certain cancer or not. There are specific DNA chips for different diseases, all based on this concept. In each well, we're going to have a different receptor recognizing different molecule. I think I will stop now. Okay? Yeah, okay? Do you have questions so far? Don't be shy. Okay? It's totally okay to ask questions. And it's totally okay to tell me, I didn't understand this, I didn't understand that. Okay? Just an introduction. You don't have to ask questions, but just for the next lectures, feel free to ask questions. Questions are the best part of lectures.
If you have question in Hindi, I can translate it.
Okay. I can even learn Hindi. That will be even better.
Sometimes they are not comfortable with English.
Okay. So that's okay. So I'll see you in the next lecture. I put this in here, yeah? Now, yeah, but maybe give them a few minutes to relax. It's very intense to sit for several hours and to listen to science. Don't worry. In my lectures, you'll have breaks between each lecture.
Hello. Good afternoon. I would first like to welcome our guest lecturer, Professor Raz Jelinek. And now it is my great pleasure to introduce Dr. Bishrup Chakraborty from Department of Chemistry, IIT Delhi. He obtained his PhD degree from Indian Institute of IACS, Academy of Cultivation of Science, under supervision of Tapan Kumar Maiti, and later on he pursued postdoctoral research from Ben-Gurion University, Israel, and later on the University of Berlin. His research achievements are well recognized. Among many honors, he has been named as emerging investigator by leading scientific journals. And also he has been selected as rising star in organic and inorganic chemistry by American Chemical Society in 2023. And above this, he also served in many editorial boards, including as an associate editor in Frontier in Catalysis. His research contribution is prolific. He has authored more than 80 research publications, 3 Indian patents, and contributed to books and book chapters. So in today's lecture, he will speak us on the topic, electroreduction of nitrate to ammonia on metal oxide nanostructure based electrodes. So please join me welcoming Professor Bishrup Chakraborty.
All right. Okay, am I audible from the back? All right, good. So anyhow, he has given me already my introduction, but I'd like to say that I'm very happy here that Professor Raj has taken his, valuable time to spend 1 week with you. So I know Professor Raj from my postdoctoral days when I was in Israel. So I know him as a very good professor, a very good researcher, but today I learned that he is also an excellent teacher. Because although during that time I have attended 1 or 2 lectures, not 1 or 2 lectures, 1 complete course in Israel, where Professor Maya Varsadan has taught us. But I came across from the students that he is an excellent teacher also. So now I got that flavor that he is a very excellent teacher. As he has already introduced, the area of nanoscience and nanotechnology and what are the futures of this nanoscience and what was the past discoveries. He will be definitely sharing some of his research achievements and also other new discoveries that is happening in last few decades. So, well, my journey is now relatively easier because he has introduced what is nanoscience and what we in IIT Delhi we are doing is also very similar in that domain. So before going into there about what we do or what is our research, I just would like to share you this slide. So those who have not visited IIT Delhi, so this is our aerial view of our institute, and this is the pointer is not working, but anyhow, this main building. This is our main administrative building, and in the top of almost all the building you can see the solar panels. As Professor Jelinek already told that harvesting solar light is also one of the major domain in nanoscience and nanotechnology. Most of these solar powers or these solar panels are made of silicon wafer or silicon nanoparticle. So anyhow, we are also trying to get sustainable energy from the solar power in IIT Delhi, and also some of you probably know that why Delhi is popular. It's popular for the pollution. All right. So what are the different pollutions in Delhi has? So we have air pollution. What is the major reason? Due to the burning of crops, and it creates also a lot of carbon nanoparticles in the air. That creates a lot of environmental issue. Apart from this small tiny nano carbon particles, we have also plenty of CO2, okay? Because we are burning the crops that is made of cellulose or some kind of carbon. So if you burn cellulose or some kind of carbon fiber in presence of water and oxygen, it will give you CO2 also as the end product. So CO2 is also a very challenging, component at this moment in environment that we need to take care of it. Okay. So apart from that, it came plenty of times in the newspaper that we have Delhi city is just on the bank of river Yamuna, right? And particularly in the Yamuna river, those who are following newspaper and concerned about the pollution, they might have seen that sometime on the Yamuna river, in the picture you have seen the foams are coming, right? The white foams on the Yamuna river you have seen might be in the pictures. So what are the cause for that? Anyone has any idea? And there are also rumor in some time you might have seen that some people thought their blessings of some god and people take a dip, they can get cure or something. You might have seen it in the newspaper. These are nothing but these are actually poisons. You know why? Because in Yamuna river, in Haryana, Punjab and a lot of districts in which this Yamuna river is passing, they have a lot of industrial belt. And during this industrial process, plenty of ammonia is being used as a basic ingredient. And during the process, after the process, they releases the ammonia into the Yamuna river, because the only way to discard is to just throw it into the river. That is the only way. So that is the reason in Yamuna river, particularly in the winter time, the ammonia percentage reach up to 8 ppm. And if you just think about human concern and environmental sustainability, the ammonia concentration in our drinking water should be 1 to 1.5 ppm. That much we can tolerate. Even less than that, I would say. Even 1.5 ppm is also too dangerous. Now that is the reason we have Delhi Jal Board, which is just beside the Yamuna river. And that Delhi Jal Board is taking care of this ammonia in addition to other nitrogen containing elements or nitrogen containing pollutant that is present in the water, or particularly Yamuna river. Now, this is a very simple chemistry is involved in water treatment. How to get rid of this ammonia. So the simple chemistry is there. If you just oxidize the ammonia into chloramine. So I am sure that most of you are from chemistry background and you know the structure of ammonia or the formula of ammonia. And what is the structure of chloramine? It's nothing but NH2Cl. That means if you replace one of the hydrogen with chloride, then it becomes NH2Cl. Or maybe sometime if you replace two hydrogen with chloride, it can NHCl2. Both are called chloramine. And in terms of activity or in terms of their caution to death, chloramine is much more greener in compared to ammonia. That is why what Delhi Jal Board, or what typically once we treat the wastewater, we treat with chlorine gas. So if you treat with ammonia with chlorine, it gives you chloramine, that is NHCl, NH2Cl or NHCl2. Now that is the only way now also how water is getting treated. Now the problem is that once we have 1 or 1.5 ppm ammonia, it can be treated with chlorine. Now once we have 8 ppm, then Delhi Jal Board raised their hand, we can't do anything. Even few days back also we got notice from Delhi Jal Board that we cannot supply water today because we have plenty of ammonia in Yamuna river. So that is a serious concern. Now that is the toxicity I am talking about ammonia, but most of you probably know that ammonia is very, very important because it is commonly used as fertilizer. And whatever the organic compound that are containing NH3, NH2 or any kind of nitrogen functionality, the only source is the nitric acid, right? If you just treat benzene with nitric acid, it gives you nitrobenzene. Now, where from these nitric acids are coming? What is the source of nitric acid? If you oxidize ammonia, you can get nitrate, and if you just protonate it, you will get nitric acid. So, basically ammonia, nitrate, nitrogen, they are in a one cycle, that is called nitrogen cycle. Even in also in biology, in plants, they have also this cycle. Now, why I am emphasizing this point, because this course is particularly for environmental nanotechnology. That means what are the molecules, what are the ingredients, they are good, or certain level if it exceeds, they are bad. Now, this is one part of the story where we need to take care of ammonia. Now, other part of the story is that, as I said, that nitrate is also an essential ingredient, because if you oxidize ammonia, it can give you nitrate, but on the other hand, nitrate or nitric acid is also an essential ingredient for industry. Now, where from these nitrates are coming? Ammonia oxidation. Where from ammonia is coming? Once we are talking about where from ammonia is coming, of course, many of you have read textbook, the classical reactions, that is Haber-Bosch process, right? How many of you have heard about it? Haber-Bosch process? Please raise your hand, don't be shy. Some of you, at least most of you. What is that? Nitrogen to ammonia, right? That is the, even nowadays also industry make ammonia from nitrogen in presence of hydrogen. And do you know what is the temperature and pressure required for ammonia making? Very high. What could be the rough range? 300. 300 is the atmospheric pressure, you need it, and you need 500 to 600 degrees Celsius temperature, and this reaction, it's not so easy. Maybe some of you have visited laboratory, you have seen conical flask, round bottom flask, and did some reflex, but these typical reactions are carried out in presence of some catalyst, and those catalysts are also having a dimension of nanometer range. I will show you in couple of next slides. In presence of that catalyst, if you heat nitrogen and hydrogen, you can generate ammonia, but the efficiency of this process is also not that much great. It can give you maximum 30 to 40% ammonia, but still this is the only process that industrially ammonia is being produced. Now, today's talk, that's why I particularly chose the electroreduction of nitrate to ammonia on some metal oxide nanostructured based electrodes. Now, then if ammonia can be produced from nitrogen, then why nitrate reduction to ammonia is important? I will come to that point, but before that, let me just show. It's not working. Yeah. All right. So before that, I just wanted to say that what else or what in general we are doing there. So one part, of course, so this in this theme, I don't know what happens. In this left hand side, some things are wrong. These are actually the products that we are targeting. So what are the products? Oxygen, hydrogen, carbon monoxide or methane, ammonia, and other part. I am sorry, there are some I think technical error is there. So that's why these reactant parts are missing. But in our lab, we are targeting mostly the water to split into these two components, oxygen and hydrogen. Now, why water splitting is also important? Because nowadays, hydrogen is being considered as the one of the green fuel, right? Why is it so? Because if you burn the normal fuel or carbonaceous fuel or natural fuel, you can end up with lot of CO and CO2. So if we can build some engine, and some engines are now available also, there are some Japan, they have already made some engine that can generate hydrogen simultaneously, and using that hydrogen they can run vehicle. So that's why this hydrogen is our next sustainable fuel. All right, and oxygen is actually our side product of water splitting, but it is also environmentally friendly because oxygen we need it because it is our only source of only fuel that we take every day. On the other hand, we have CO2 in our environment, which is coming from environmental pollution or some kind of industrialization, lot of fossil fuel burning. So we have CO2. So CO2 to CO or CH4, if we can make it, so there also we can convert this invaluable or toxic CO2 into CO and CH4. And similarly, as I said, that nitrate can also be converted into ammonia, because sometimes although nitrates are essential, but high concentration of nitrate is also found in water, and that are toxic for us also. So that is why nitrate to ammonia is also a sustainable conversion, and it can also bypass the Haber-Bosch process that we are going to discuss again. And the fifth one is the conversion of ammonia to NOx or N2. So these are their abbreviations. The first one is the oxygen evolution reaction that is coming from water splitting, and another component is the hydrogen evolution reaction that is also part of that reaction. CO2 to CO and CH4, that is abbreviated as CO2RR, that means CO2 reduction reaction. Fourth and fifth are NO3RR, that is from nitrate reduction directly to ammonia. And the fifth one is the oxidation of ammonia to NOx or N2, that is known as ammonia oxidation reaction. So in our lab at IIT Delhi, we are mostly focusing on these 5 different reactions, where in the left hand side, although it is not visible, we have taken small molecules like water, CO2, nitrate and ammonia to convert them into valuable products. So what are the valuable products? Hydrogen is the essential fuel nowadays, CH4 is also required, ammonia and NOx. Now in this conversion, we are normally using a catalyst and light or electricity as a source of energy to convert them. So that's why we have, in our lab, we are mostly converting photoelectrochemical conversion of these small molecules into these valuable products using inorganic nanomaterials as the catalyst. So basically what we are doing, we are developing some nanomaterial as the photocatalyst or as the electrocatalyst to convert them into these invaluable products. Now, what other things we must know once we are doing catalysis? So these things is that, let's say in this schematic diagram in the right hand side, you can see this red tube. Let's say if it is a catalyst. So what is catalyst? Catalyst is I think most of you know, it can be a compound, it can be a nanomaterial, it can be a molecule which accelerate the rate of the reaction from the reactant to product and remain unconverted or unaltered. Okay. But in some recent examples, there are incidents you can find that catalyst either cannot change their structure, or sometime they can change partially their structure or completely their structure. In this case, I can call it's a catalyst, but in the lower two cases, I cannot call it as a catalyst, I can call it as a pre-catalyst. That means if some structures are derived from this thing and this is the actual component of taking part in this catalysis process, then I can call it as the pre-catalyst and partial conversion is happening. So our main target is that we want to develop some earth abundant metal based catalyst or earth abundant element based catalyst to study their activity and also study their stability. Next thing is that whether this catalyst is stable under the catalytic condition or turnover condition, and to understand what is the chemical structure of the catalyst and how its structure is directly can be correlated to the activity of it. The third thing is that how on the surface or how this catalyst is absorbing the reactant, converting step by step. That means whether we can predict the reaction mechanism, because there must be some elementary reactions or multiple steps involved in one of these reactions that are presented in the left hand side. So, these are actually our targets. And now, before I move in to the directly to the things, I would just like to share that these are my students who are actually working, and I am only presenting and guiding them. So, in these first 3 students, they are already graduated. So, for today's talk, I will be mostly talking this third student, Lakshmikanta, who has developed this nitrate reduction to ammonia in electrochemical condition, where you can at room temperature you can convert or you can prepare ammonia, and how you can bypass the Haber-Bosch process. And now I will just start from here. Although my animation is not working, otherwise I could have asked you to correlate these 4 pictures on the top. Although the answers are given. So, top left is Professor Friedhaber, second is Professor Karl Bosch, third one is the reactor that has been made by BASF company. It is a German company and one of the ancient company. And in this picture, you might be, if you can see, there is a big steel tube is there, and this is the first high pressure, high temperature reactor has been made in BASF. And in this reactor, they had catalyst which is made of iron. So, actually in some of the talks I used to ask students that can you correlate these 4 pictures. So, correlation is that this Professor Friedhaber is the first person who discovered the ammonia production in the laboratory. Now, there is a story behind it. I just like to share. The story is, so after the First World War, there was a huge crisis of nitrate, because you know nitrate is the only ingredient that you need to make gunpowder, because in World War you have to have gunpowder with you, a good stock of gunpowder. Now, at that time, the only source of nitrate was South America, somewhere in Chile, and we have in India we have also plenty of stock in nitrate, but unfortunately India was under the control of British. So, German has clashed with them, so they cannot access the nitrate from India, and also similarly America was against German, so they cannot access the nitrate from there also. So, that is why the German government thought, let us synthesize nitrate in laboratory and then it translate in a bigger scale or ton scale in our own country, although we do not have nitrate source. So, in this vision, Professor Friedhaber was working, and he made a remarkable discovery that nitrogen, once react with 3 hydrogen molecule, it can give you ammonia in a certain quantity under a huge pressure of 300 bar and 500 degrees Celsius. And he found it out there is a mixture of catalysts which can be iron, iron oxide, K2O, calcium oxide is required, and it can convert into ammonia. And for this remarkable discovery, he was awarded Nobel Prize in 1918. Later on, because whatever he has made in a laboratory scale. That means 1 ml per hour is was the production rate. But after 1 ml production of ammonia, if you oxidize ammonia to nitrate, it will give you very trace quantity of KNO3 or NaNO3. So, it would be no longer useful for making the gunpowder. So that's why Karl was taken into the action. So he translated this discovery into industrial scale, in a ton scale per hour. So that's why later on he was also awarded Nobel Prize. And now after this discovery, German people successfully developed this ammonia to nitrate, starting from nitrogen as the precursor. So from then onward, this one step or this simplified reaction becomes landmark discovery in the science. And nowadays also in industry, people are doing the same conversion with some modified reactor, not like this ancient reactor that is still in BASF. So here is the history of ammonia production. Now if I just go towards the thermodynamics of this ammonia, then why, I don't know, some of the arrows are not working here, maybe due to some technical issue, but why we need to now at this moment bypass nitrogen reduction to ammonia. First thing is that it's very simple, that if I take a nitrogen molecule, nitrogen is having a triple bond in it. So essentially it is very high dissociation energy is involved, that is around 941 kilojoule per mole if you want to break down nitrogen into ammonia. Similarly, if you notice the previous example, there the catalyst that has been taken is a solid phase catalyst, and now nitrogen and hydrogen, both of them are gaseous phase. So that means we are talking about a heterogeneous phase reaction. Now for the heterogeneous phase reaction, the rate determining or rate limiting steps are basically the adsorption of the gas molecule on the catalyst surface. So here are 3-4 primary limitations once we are talking about Haber-Bosch process, but still I can say there is nothing can beat this NRR or ammonia production by Haber-Bosch. We are just trying in the laboratory scale. Now what is the alternate? In the alternate is that, as we have said, as I have said, that we have plenty of nitrate, and nitrate is also equally abundant on earth crust. So nitrate can be the essential precursor for making ammonia. And if you just look into the simplified reaction, that nitrate reduction requires 8 electron and 9 proton to convert ammonia. On the other hand, nitrogen reduction is technically simple because it has 6 electron, that means 2 electron less. Now if you look into this correlation chart, that means oxidation state versus reduction potential, if you have read the textbook or if you have already graduated MSc, then you must be knowing that redox potential is directly related to some reaction and its chemical equilibria. So if I want to do nitrogen reduction, it needs only 6 electron. If I want to do nitrate reduction, it needs 8 electron. That means electronically a number of electron requirements in nitrate reduction is higher, but still nitrate reduction is thermodynamically more feasible. Why? Because of this thing, the NO bond dissociation energy is 2-3 times less than the NN dissociation energy. On the other hand also, KNO3 has a high solubility in aqueous medium. So if you want to do the reduction in solution phase, you are good. You can use nitrate and you can do the reduction. And similarly, since nitrogen is chemically inert, it is very difficult to get adsorbed on the catalyst surface, whereas NO3 minus in plenty of cases, even molecular complexes, heterogeneous surface, you can see that the nitrate can easily get bound to the surface. That means binding of the nitrate is also favorable. So with this thing, we can say that the NO3RR, which is the short form of nitrate reduction, is thermodynamically slightly more preferable than NRR or nitrogen reduction. All right. Now let's look at how these reactions occur. Oh my God, I don't know. There are some issues. some camera figure was there, that's why it is not appearing. So anyhow, let me just help you to explain. So let's say how the reaction occurs once you do the chemical reaction. So typically if you have a catalyst, so that means a catalyst must be having some surface. Now as I said that once the catalysis occur, the reactant, here we have taken nitrate as the reactant, and nitrate get adsorbed in this side, this. Oh my God. All right, so this dotted line indicate that the nitrate is coming from the top and it is attached to here. And this particular steps, we know it as the adsorption of nitrate. Now later on it has been observed that this reaction does not occur in one go. It needs some sequential reactions. So in the first step is the adsorption of the nitrate on the surface. In the second step is the first 2 electron reduction and 2 proton involved there. It gives you nitrite, although the structure is missing here, but please assume that here is a nitrite, that means NO2 minus, which is attached to the catalyst surface. And in the subsequent step, it is involved multiple electron and proton coupled reaction to give you the corresponding ammonia plus water. Now why I have highlighted this particular yellow section? Because these are very, very crucial to control the rate of the reaction on a heterogeneous surface. Now if you look further detail into the process of nitrate to ammonia, we can find it out, as I said here, this adsorption on the catalyst surface. Since we are doing electrochemical reduction, so we need an electrode, and there on the top of the electrode we kept catalyst loaded, and nitrate has to come and bind. I think it's pretty sensitive, the screen is sensitive. Yeah. So nitrate needs to come and bound to the catalyst surface, and then this RDS means is the rate determining step, that how it is bound to the surface and how it is converting to nitrite then, because as I said that these two steps are very, very crucial, that whether the catalyst is very nice, that means it is very fast, it is giving good adsorption or so, and now after that there are multiple possibilities. What are the multiple possibilities? It can take up electron, proton, it can generate to nitrogen. So if I convert nitrate to nitrogen, then our actual process is not succeeded. On the other hand, if you do stepwise electro reduction, then you can end up with nitrate, but there is a chance that you will be losing your sum of the product if you cannot control the pathway towards either this or towards this. That means we have 4 parallel pathway for nitrate reduction. Now if you cannot build a very selective catalyst, that means if a catalyst can selectively perform your nitrate conversion through this pathway or this pathway, then only you can able to make ammonia on electrochemically, through electrochemically on a heterogeneous catalyst surface. Now other difficulties also, because as I said that the reaction although looks very simple, but it did not or it do not occur in a very simplified manner. You have a possibility that you can lose in the middle and it can end up with some other product. Other product is also there, that is the hydrogen. I'm again sorry for this thing because some technical glitch with this computer and my pen drive, that's why some of the things are not appearing properly. But here I have just tried to mention that once we are doing a reduction of nitrate to ammonia in aqueous medium, there is a high possibility that you can end up with reduction of your water to hydrogen. Although hydrogen is good, but in this process we need ammonia as the only product. So that is why nitrogen nitrate to ammonia is although very demanding, but on the other hand it is very challenging to do, because you have a chance that you will not reach to your target product. Okay. Now, regarding the catalyst design. Now, what kind of catalyst would be more beneficial for us? First thing is that catalyst must be very reactive. Okay. Second thing, it must be cheap. That is also one way. So that's why I have given you this schematic diagram, where in this triangle, these three vertexes are the efficiency. That is the one parameter of a catalysis. Efficiency means once we are doing electrochemical reduction, that means the operating potential, that means how much in terms of energy, how much less energy you need or how much more energy you need to convert this. And second thing is that kinetics, that means how fast the reaction is occurring or how slow the reaction is occurring. Okay. So these are the two thermodynamic parameters. Now second is the economic part, that means cost part. So if you, let's say if you build up or if you make a catalyst out of platinum or gold, then I must say that you are very rich chemist. So that means you need a earth abundant metal, and catalyst must be made of inexpensive sources or inexpensive elements. Now last part is the sustainability or stability. That means if you have made a catalyst, it just lasts for one day, and after one day your catalyst get degraded, there is of no use in industry. If you go for industry, you need at least 1 year, you have to run the catalyst, and then only you can recycle it. So this is why that performance matrix has to be very strong. That means catalyst has to be recyclable. So that's why if you want to build up a catalyst, you must be maintaining this triangle perfectly aligned to make it a perfect triangle. Now in practice, again there are some missing things here. In practice, it has been observed that the ruthenium, platinum and iridium, these three metal based catalysts are the best electrocatalyst. Why? Because their efficiency is the maximum and stability is the maximum. I intentionally draw this triangle imperfect to show you that the cost of the catalyst is pretty higher. So if cost is very higher, then that means this ruthenium, iridium and platinum, although their performance is very excellent, but they are not sustainable catalyst. Now in this particular chart or this plot, I have just shown you that just to correlate this triangle with this natural abundance of the element, there are certain region. So this green region represent that which elements is highly abundant or the earth crust. Now if you look into this yellow region, that means abundance is pretty lower. In that region these three metal arises. That is why if you, let's say if you go to a laboratory, you will be finding that if you want to purchase platinum salt or ruthenium salt, 1 gram of the salt can cost around 20,000. So you must be thinking or you must be taking care of the cost of the catalyst. Now the thing is that why noble metal are best, because again the diagram is missing. Let's assume that here you have a nitrate molecule and here you have the metal. Now if you just take NO3 minus and one of the oxygen is coordinating to a metal center, and I have drawn it here the orbital diagram that could have helped you, but unfortunate thing is that it's not working here. If you have a metal rich of electron, then the pi star of the NO has to be coordinated back with its pi electron, so that the bond dissociation energy drops. That means in order to do nitrate reduction, you must be taking a metal catalyst which is having rich of electron, so that you can reduce the pi dissociation energy, giving back the electron density here. So that is why you need a electron rich metal. That is the bottom line from this slide. Now what we are looking for? So as I said that we are looking for basically earth abundant element based catalyst, and so far we have taken this part of the periodic table where these are the 3D elements we have chosen as the precursor, and these are the 4D and 5D element as we have chosen, and by doing simple permutation combination we can build up this wolframite type bimetallic metal oxide. Okay. As I said, these reactions are pretty simple. If you just take this precursor and put it in a normal reaction condition, you can end up with this wolframite structure, and this indicate the one of the unit cell of the catalyst, and this color code indicates that it has two metal center in it, and that is why I have given that these are bimetallic oxide. And the advantage of these two metals are that you have redox active metals which are these 3D elements, and molybdenum and tungsten are also redox active, but here they are having plenty of electron density present in them. Now on the other hand, if you just do or if you change the reaction condition, you can end up with some molecular clusters. These are not nano structure, these are relatively less in size, less than 1 nanometer their structure. So their molecular cluster also you can prepare out of these 4D and 5D elements. So they are commonly known as polyoxometalate because the multiple metal oxo centers are connected with each other through oxo bridging link. So these also we prepare in our lab, and also we made some metal sulfide. That means if you take a metal salt and if you take any kind of chalcogenides, let us say sodium sulfide, and if you just do some reaction, you can end up with metal chalcogenides inorganic compound. So this 4 or 5 different material we are preparing in the lab, or we have prepared in our lab, and once we have characterized them, we find it out that their morphology and structures and other thing actually fit into the nano domain. So that is our actually primary target of this course. So that is why I prefer to take you here that this two kind of structure for today's talk I will be talking. One is the LDH, that means layered double hydroxide, and another is the polyoxometalate stabilized metal oxide core, because both of them are having a dimension of nano regime. All right, and we are particularly focusing on this nitrate to ammonia conversion. Oh my God, again some of the figures are missing, but these two pictures were taken at BGU. These are my during my postdoctoral study. Here I am trying to give you a flavor, a simple experiment. Let us say if you went to a lab and if you have taken ferrous sulfate in an aqueous medium, so what will happen? It will give you a colorless solution. And why it is colorless, or why there is no precipitate in it? Because the iron salt is very soluble in water. Now if you just check the pH of this solution, you will be seeing that pH is around 2 to 3. Okay? There is nothing bad in it, because all the ferrous or ferric salt, they are aqua acid, so they will give you the pH relatively 2 to 3. Now the point is there, if you just start adding sodium hydroxide or any kind of base in it, you will be start making insoluble ferric hydroxide. As you can see here, this is the logo of this BGU is visible, whereas once you have added NaOH and if you made the pH 7, everything is getting orange cloudy solution. Now what chemistry is behind it, or what is happening here? Now what is happening, although the scheme is missing, once you have taken a ferrous salt, that means in aqueous medium, iron is surrounded by with 6 water molecule. This is simple coordination chemistry in it. Now, once we are raising the pH towards 7, you are adding hydroxide into it. And why then color is orange? Because in water we have plenty of dissolved oxygen, and water medium, it gives you oxidation of iron 2 to iron 3, and all the way around you have a lot of hydroxide in it. Now, it gives you coordinate replacement of water with hydroxide, and as we know that hydroxide is a good bridging ligand. So, it started bridging with next iron atoms. Now, slowly, if you cannot control this bridging process, it will end up with all of a sudden a precipitate that is commonly known as amorphization or amorphous precipitate. Okay. And similarly, if you just look into the aqueous speciation chemistry, you can find it out that in pH 6 to 7, iron is mostly insoluble in nature, right. And now, the point is here, although it is not part of nanotechnology, in our blood we have plenty of iron, and our blood pH is around 6.8 to 7.2. Now, then what is the reason that iron is not getting precipitated out? What is there to protect us? To protect us, we have protein, all right, and proteins are made of amino acid. These are amino acid polymers, and they are protecting the iron. And there is one specific protein which is very important for us, that is called ferritin. I don't know how many of you heard about its name. Now, why I am taking this name of this protein? Because the ferritin is a hollow protein, and if you look into its structure, or if you just check the textbook, you will be finding that it has a hollow shell. Inside the hollow shell, you have iron atom preserved in +3 oxidation state. Other than this protein, iron is present in +2 state in almost all metalloprotein. So, except this protein, you will be finding iron 2, because iron 3 is toxic for cell. Now, important thing here is that in this protein, inside the structure or inside the protein, you can store 3000 to 4500 iron atoms at a time. And another interesting fact is that many of you have seen rust, right. If you keep an iron bar in water and oxygen, it gets corroded immediately and it give you rust. So, what is the structure of rust? It actually having a very similar structure what is present in the core of the ferritin. Now, if you measure the ferritin structure, you will be finding the ferritin is having a dimension of 1.2 to 1.5 nanometer. So, which is slightly relatively less in size, but it is also close to the nanostructural regime, and the core structure of ferritin is having a similarity with the rust structure, and that is the structure of actually the insoluble form of the rock, which are basically iron oxide. So, one of the structure like this one is having a structural similarity with ferritin, and also this during this experiment what you are making this FeOH whole thrice, if you just slightly warm this mixture, you will be ending up with beautiful crystalline material with nice edge sharing structure, and if you control their structure with some surfactant or with some ligand, you can make nice nano structure of iron oxide or iron oxyhydroxide. And these particular 4 polymorph means they have a similar composition but different packing in the 3D packing. So, that is why you can see they have a different packing, and this is the iron oxyhydroxide. Why these are important? Because these 4 structure or iron oxyhydroxide are very reactive in compared to the stable form of iron oxide minerals like hematite or magnetite. Now, what I am just showing this slide because in our lab we are trying to synthesize some of this insoluble iron oxyhydroxide nanostructure core completely dispersed in water in presence of some inorganic or organic ligand. And another thing is that in the second slide I have shown you that this iron is the only metal which has been used to convert nitrogen into ammonia in the Haber-Bosch process. So, that is the reason we have chosen that iron as the one of the metal for converting this. Now, let us look into the some literature study, because once we are starting some research you must be looking into what is there in the literature. So, here as I have already shown that there are plenty of possibilities of having nitrate to ammonia conversion. Some of the literatures are known that this delta form, there are 4 different polymorphs are there. The delta form is one of the active form of iron oxyhydroxide, and it can nicely bind this nitrate on the surface, but nothing till now known that how this delta form of FeOH convert ammonia from nitrate reduction, okay, because it is quite unknown that how it is getting converted on the surface of delta FeOH. So, that is actually triggers our mind that let us look into this particular material and let us look deeper that how we can predict the reaction scheme on the surface. And that is why we took some different form of iron oxyhydroxide, and already in the last 2 years back we have seen that if you make the crystalline form of gamma FeOH, polycrystalline form of gamma FeOH of 2 different category alpha and gamma, there is a competition, and in this competition we can see that the amorphous form or the polymorph of the gamma form, polycrystalline form, it actually gives you better result once you put on the surface of that. So, that actually helps us to choose this gamma FeOH as the one of the important material for us, and we again, okay, something is missing, but this is nothing but a ferrous salt. So, that is why we took ferrous salt as the precursor, and we tried to prepare different form of iron oxide. So, what are the different form? One is the polycrystalline form that we have made. Just simply if you take ferrous salt in ferrous sulfate form, 24 hours room temperature if you prepare, some cloudy orange precipitate will come out. If you just put it under the microscope, you will be finding they do not have a definite surface boundary, and they are commonly called as amorphous, or sometime if they have some partial crystallinity, that can called as a polycrystalline gamma FeOH. Now, if you heat them slightly higher than room temperature, that means 75 degrees Celsius, you can see there is no other surfactant or any other molecules are present, and you can build up very nice nanoplates. Nanoplates where? Why? Because you can see there are, sorry, it's very sensitive. These are having a dimension of little more than 100 nanometer, these individual plates. And on the other hand, if you just heat them slightly higher temperature like 190 degrees Celsius, the phase completely changed to alpha Fe2O3, that is actually the hematite, and the shape of this material is also like a flex kind of structure with having a dimension of 100 nanometers. So, in this we can make some nanoparticles of iron oxide in 3 different form. So, one is nanoplate kind of morphology, another is nanoplate, and the first one is the polycrystalline gamma FeOH. So, these two are nanostructure and these two is a amorphous material. Now, these are the image that we got from some microscope. So, Professor Raj already told you that for the nanoparticles we cannot use optical microscope. So, these are taken under electron microscope just by doing some normal electron microscope. And another study we have done. So, these are their individual particles. Now, once we are doing electrochemistry or catalysis, you must be looking at the surface. So that's why we took a contact angle measurement. So I'll tell you what is contact angle measurement. We take the bulk material, we paste them as a film, and we drop casted water in it. Now this is a basic surface tension and viscosity, you have read it in your masters, that a surface, if it is having a higher energy, it will, and if it is hydrophilic in nature, it will absorb water or aqueous medium very fast. That means you can, if the surface is hydrophilic, you will be getting a acute angle, right. So 24 degree is the acute angle that we got for this gamma FUH crystalline, that is this one. Other angles I am not showing, but they appeared as almost hydrophilic in nature, but there is a slight difference in their contact angle. That means that all these three material, their surface energy is close comparable. So that we can conclude from this study. Now the next study what we did, next study is this adsorption, gas adsorption desorption. Once again I have said these are all surface measurement or surface characteristic. So in this gas adsorption desorption, this isotherm, these are known as isotherm, there are some technique in which you take your powder sample and fill it with gas at low temperature, how much is the volume change, that gives you the idea about the surface. So from there we can identify that this gamma FUHC, that means this one, the crystalline nanoplates are giving a relatively higher surface. So as we know that higher surface means higher probability of adsorption of your analyte. So from this study we can conclude then that this material is having a higher surface and also higher surface energy. Next thing is also another technical term, that is double layer capacitance, that is coming from electrochemistry. So I will not tell the details because it will take some time. The observation is here again is very similar. Now once we have these three nanostructure material, you can find it out, the slope is steep for gamma FUHC, that means the crystalline form of gamma FUH is having, again electrochemically once we have determined the surface area, that is also higher. All right. Now oh my god, anyhow I don't know how to present this because everything is lost here. Do you have a spare laptop? Maybe I can connect it. Although my time is very short, but anyhow let's, I don't know, because these are some important files that I wanted to show. Can you quickly connect it? I think I'll just from here. इसको ओपन कर दो. Yeah, all right, it's coming in there. All right. Sorry for this interruption. All right. So I went again from here. So here from this slide we can conclude that this particular gamma FUH is, as we have proved, that it has a high surface energy. Now since our main intention is to do the electrochemical reduction of nitrate to ammonia, so what we did, we just have taken all these three material and put it on the electrode surface one by one, and we polarize the electrode towards negative direction. Now what does it mean? It means that now electron is flowing from this electrode to catalyst, and whatever the analyte is getting absorbed on its surface, it is giving the electron. So that's why in this particular plot what we have done, that we have varied the potential of the electrode from positive to negative. That is the bottom line here. And we have just recorded that how much current or how fast current it is flowing through it. And this is typically known as the linear sweep voltammetry. So where we are changing the potential of one electrode towards one particular direction. And here, since we have moved from positive to negative, that we commonly call as cathodic direction or cathodic process. So in this cathodic process, what is happening? The electron is flowing through electrode to catalyst to the analyte, so that we can reduce the nitrate to ammonia. Now how to interpret this data? Interpretation is very simple. Just from a basic sense I can say that whenever we can reach most negative electron or most negative current density, that gives you better activity. That's how a layman can interpret. So from this, in a particular buffer pH 7, because the nitrate is mostly soluble there, you can take the competitive or comparison as the mark to check the activity. So here you can see that the gamma FUH, once you have the nitrate in the electrolyte, you are getting highest current, and this dotted line is representing that once you do not have any nitrate in it. So that means once you have nitrate in the electrolyte and catalyst is gamma FUH, you are getting highest catalytic current. That means there are catalytic conversion of nitrate to ammonia. Now just to prove further that nitrate reduction or this current is due to the nitrate present in the electrolyte, you can vary the concentration of nitrate, and you can correlate that with the variation of the concentration your activity is increasing. And here is the linear correlation, just log J log nitrate. There are some little bit of mathematics, and from there you can get the expression that how nitrate is participating in the rate of the reaction, and from this we can say that nitrate, the order of the reaction with nitrate is 1. So these are simple electrochemical experiment. Another experiment we did, instead of having a static electrode, we just rotated the electrode because of there are some inner process, some diffusion control process, just we want to avoid that part. And we have seen that the rate of the rotation of the electrode is directly related also to the reaction, and from there we can also analyze, just forget about the equations or something, just take the chemistry behind it, that from there we can again get the idea that how many electrons are actually involved in the rate determining or rate limiting step. So this experiment is saying that in this process, once the catalyst is gamma FUH, your rate limiting step is the first 2 electron reduction. So that means once you are converting nitrate to ammonia, the nitrite is forming as the rate limiting species, and it is actually controlling the overall reactions. So that's what we understood from here. Now once we have, as I said, that I have taken 3 different material with 3 different morphology and 3 different surface energy. So we must compare their activity in terms of Faraday efficiency. That is one term by which we determine for a simple chemical reaction, how do we know that the chemical reaction is very efficient? That is the yield. And in electrochemical process, we represent it as the Faradaic yield or Faradaic efficiency. That means how many electrons you are giving and how many electrons actually you are giving, it is participating in the reaction, and that fraction is represented as the Faraday field. So, maximum Faraday field means maximum efficiency of the catalyst. So, here from this bar diagram, this red y axis is the Faraday efficiency, and you can see here that gamma FUHC, that is the crystalline form of this gamma FUH with this layered structure, is giving the best yield. On the other hand, this sub y axis is the yield rate, that means how much amount of ammonia is being produced per hour. So, it gives you a amount that is almost 18 mg, 18 milligram per hour per centimeter square, because we have taken a 1 centimeter square surface area of the electrode. So, these matrices we have got, and from there we can conclude that this is the best active catalyst. We have screened other possible options also, varying the pH, varying the concentration, and we got that this is the 84% is the highest possible ammonia we can produce with 18 mg per hour is the rate. And also, once you are doing this kind of thing, you must prove that your ammonia that is you are getting in the process is actually coming from nitrate, because you have nitrogen in the environment that can be also present in your electrolyte. So, that is why what we did, we just replaced normal nitrate with level nitrate. Level nitrate means we have taken 15 isotope containing potassium nitrate as the electrolyte, and we did proton NMR. Okay, some of you, if you are PhD student, then you must be encountering this kind of proton NMR, I assume. So, once you have 14 nitrogen in your ammonia, it gives you splitting of these 3 peaks, that is because of 14 isotope. Once
the carbon dots, little carbon nanoparticles, can have different colors, beautiful colors. There is a good reason for these colors, but we can do magic for them. For example, we can take the carbon dots, use the color to image cells and vesicles. You see these beautiful colors we can get from labeling using these carbon dots, label these vesicles and get different colors. The carbon actually is a member of honor of the nanotechnology world. We can get different carbon nanostructures, pure carbon nanostructures. The first one that was discovered about 40 or 50 years ago, and somebody got the Nobel Prize for that, is called C60 or fullerene. Just like a ball, football. In India you say soccer or football? Football? Like this, yes? Okay, so this is the football. This is a nano football made of just carbon. Pure carbon organized in a very symmetrical way. Very interesting chemical and physical properties of this nanostructure, which is called fullerene. For example, you can use fullerene and make a transistor. This is the fullerene. This is one electrode, two electrode. When the fullerene is there, you can get different currents going through. This is a transistor. You can use fullerene as a lubricant, just like oil. Put the fullerene between two layers of material, and it will be smooth surface, just like a lubricant. And of course, there's various variations of this fullerene. Now, we saw many different things and interesting things about nanostructures and nanomaterials and nanotechnologies. Now, one important question that you can ask, okay, it's very interesting. Can you make money out of this? Making money is very important in life. It's not the most important, but it's also important. So what I'll show you now are a couple of slides with actual products and companies that people made over the years from nanostructures. So for example, here we have artificial cartilage. You know, sometimes you get problem with your knees, you have to replace your knees or replace the cartilage in your knee because it's just like very bad. So artificial cartilage, that's an actual product that you can not buy, that doctors can buy and put in your knee, is made from nanoparticles. And again, as I showed you these lubricating properties, this is what you can do with them. You can get various composite materials from nanoparticles and nanomaterials. For example, airplanes now. You can build lighter airplanes from nanomaterials. This is a nanogel. This is actually a sunscreen or a cream that you can make from nanoparticles. Because you have nanoparticles, we're going to talk about it, they can penetrate very easily through your skin and then protect your skin or serve as a medicine. Solar cells now, we're going to talk towards the end of the week about nanotechnology and solar energy. Now you can make giant solar cells. This is very big. This is not nano. This is macro. But these materials, when you look inside, they are made from nanomaterials. So, you can make money. That's good. That means that you should listen very carefully to this class, this is course, because at the end you might know how to, maybe you have some ideas about how to make new products using nanotechnology. Now, what's the future? What's the future of nanotechnology in general? Okay, so one thing about the future is that you cannot predict the future. The wisest people on earth have difficulties predicting what's going to happen next week, next month, next year. This is exactly the case with nanotechnology. For example, you remember this guy, Richard Feynman, the guy that we talked about in the first slide or so? In his book, remember, it's all started from this book that he said there's plenty of room at the bottom. So in his book, Feynman wrote 2 challenges. He said, if people ever can do these challenges, then the world of nanotechnology will be here. And these are the 2 challenges. He actually thought that these challenges, maybe it will take 50 years to do. But let's see what happened. The first challenge that Richard Feynman wrote in his book was, if it will be possible to build a motor that will be so small, 1/64 of an inch. This is like 10 micron motor. Very, very small. When Feynman wrote his book, it was something totally unbelievable, unimaginable. But he wrote it in 1960. In the same year, some people succeeded to do that. It gives you an idea about the human ingenuity, the human innovation. He set another challenge. He said, what will happen if it will ever happen that you can write the entire Encyclopedia Britannica. Do you know Encyclopedia Britannica? Well, nobody's reading encyclopedia these days. Encyclopedia Britannica is not one book. It's about 100 books, each one 1,000 pages, and it basically describes everything that there is on Earth, geography, history, art, everything. 1,000 books, 100 books. 1,000 pages, 100 books. And the challenge was, let's put all of the Encyclopedia Britannica on the head of a little pin. If you succeed to do that, this is going to be nanotechnology. Now, he made the challenge in 1960. In 1985, people used a technique called electron beam lithography, and they succeeded to write the Encyclopedia Britannica on a pin. You can see one page of the encyclopedia. So we can do anything we want, almost. So this is one prediction of the future. This is actually, I took from an article that appeared in about 1998. It's an old article. This article talks about how chips are going to get smaller and smaller. So this is according to the prediction. These days, you can actually get chips that are here. The capability to make smaller and smaller chips, remember the nanowires I showed you? Using that, you can make now chips that will be based on quantum phenomena that will be extremely, extremely small and fast. Nanotechnology patents. You see, there's more and more patents, more new things invented. Right now, this is 2005, 10,000 patents about nanotechnology a year. I'm sure now we reach maybe 100,000 or million patents a year. So to conclude, it's too early. I need to talk another 15 minutes. I'm joking. So what did we learn in these 2 lectures? We learned that nanoscale materials exhibit very interesting properties, distinct chemical and physical properties. We see that nanotechnology has an impact in diverse fields, in chemistry, in engineering, in biology. You know what? Even in art. But we're not going to talk about it here. There are new scientific, technological, and commercial applications. And that's it. That's it for the introduction. Questions? Yes? Thank you. From what?
From knee pain.
Ah, knee pain. Okay, yes. I'm sorry for her, yeah.
You told about artificial cartilage.
Yes.
So I wanted to know that, is it in use? And if yes, how prevalent it is? And will it ever come to India?
Well, I don't know the details, but I'm sure if you search in the internet, there is a lot of, it's called artificial cartilage. Some of the artificial cartilage that they sell as products are made of nanoparticles and nanomaterials. In many cases, the companies that make it, they're not telling you what it is because it's like a trade secret. They make it in their labs. They don't want anybody to know, so they're not going to have competition. But it is made of nanomaterials. So what I suggest to you, or to your doctor, or to your grandmother's doctor, if you can just search for products in the internet, or type keywords, artificial cartilage nanomaterials, and you'll find various products. Good luck to her. Okay, everybody. No more questions. So we'll see you tomorrow. Yes, sorry. Yes. Okay, DNA chips. So we have a few minutes, I'll talk some more. In many cases, when you have genetic diseases, to find out the actual disease, what you need to do, you have to find which genes are defective, which genes have problems. Now, in our body, in your cells, there are thousands of genes. So how will you find what is the bad gene? How will you find what genetic disease do you have? So what people do, actually, let me just go quickly here. What people do, or what the companies do, they take this chip, and in each well here, they put a little sequence of oligonucleotide. Oligonucleotide, these are the building blocks of DNA. Each of the oligonucleotides here is different, and each one recognizes a different gene. Each one will bind a different gene. So what do you do? You have here maybe 1,000 markers, binders for specific genes. And then you take a drop of blood and you put a drop of blood here, and you shake a little, and the genes that are defective, because each well can target a different gene or different defective gene, the genes that are bad will bind to the different wells, and you look under the microscope. It's not a microscope, you have a camera, a very fast camera, and you will find here there is binding, here there is binding, here there is binding. If you see this binding, maybe you have cystic fibrosis. If you have here, here, and here, you have another disease. Sometimes you can use this for detecting cancer, for example. And you could do that only because you made these wells so small, nanoscale cells, that you can, in one chip, you can screen for thousands of genes in 1 minute. This is the idea about DNA nanochips. Okay? Very nice. So, see you tomorrow. Yeah.
Yeah. All right. Okay, you want another 2-3 minutes? Yes? Okay. I'll then. All right, I'll then go back here again. All right, let's start. Okay, so this part of my talk, I'm going to cover another important electrochemical reactions. In the last part, as I have discussed, that nitrate to ammonia is one of the essential nowadays, electrochemical conversion that we really need to look into it. But before ammonia, of course, we need to also think about another alternative source of energy, that is the hydrogen. So in the last lecture, I have given you a very brief idea that what are the main reactions actually we are looking forward. Unfortunately, that time the images were not very clear, but here you can see. So the idea here is that again we are using these small molecules like water, CO2, nitrate and ammonia and converting into them the essential compounds like oxygen, hydrogen and other things. And in those conversions we are using some kind of earth abundant catalyst, and as I have discussed that what is catalyst and what is the essential role. Now in this portion of my talk I am just mostly covering this water to oxygen and hydrogen. That means in one reaction we are oxidizing water into oxygen and reducing water into hydrogen. Now how electrochemically we can do it? Now before we do it in electrochemically, let me ask you, how many of you have read photosynthesis in your higher secondary? Almost all of you? Okay, great. Now let me go into much detail. What is the enzyme that is responsible for water oxidation in photosynthesis? Any idea? Metalloenzyme or anything? Okay. Photosynthesis 2 or photosystem 2. Okay. Now if I go further detail in photosystem 2, and if some of your MSc course or maybe BSc course, if you have bioinorganic subsection, you might be having some idea that in photosystem 2 it's a very huge bulk biomolecule, and if you just measure its dimension it must be in a nano dimension because it's a protein molecule and in that protein molecule there is one important metal cluster is present, okay, and that metal cluster which is attached with the protein fragment, it actually convert water into oxygen. And now as most of you know that in photosynthesis there are two different reactions are there. One is water to oxygen, another is CO2 to glucose. And we know that one is photochemically driven, another is only chemically driven. Now in photochemically driven reaction also there is one small molecule that is involved and it is present in large quantity, and that is chlorophyll. It is actually photosensitizer. Now if you just stack this small chlorophyll molecule in a sequence, it gives you a very big giant cluster kind of stuff. It's commonly known as anthem, okay, and it harvests the visible light, okay, and once it harvests the visible light, it slowly oxidize the manganese cluster into high valent manganese state, and it gives you a very strong oxidant which is very similar like manganese dioxide, okay, and it oxidizes water to oxygen. Now in this particular photosystem or photochemical reaction, water is getting oxidized to water, oxygen, and it releases 4 electron and 4 proton. Now the idea here is in electrochemical water splitting, if you couple this 4 electron and 4 proton, you can generate hydrogen. But in natural process, these 4 electrons and 4 protons are being used to reduce CO2 to glucose, and that is also an essential reaction, because without that we will not survive, because oxygen is our fuel and glucose is our food. So in photochemical process we are basically generating two important stuff, one is oxygen, another is glucose. Now nowadays, or let's say since few decades, people are looking into this photosystem or photosynthetic model and trying to mimic them in the laboratory, but in a different way. What are the different way? Either you can build a catalyst which can be made of some nanostructured material, or it can be a catalyst of smaller molecular complexes. But the problem with the molecular complexes is that for long term process they may not survive. So that in that sense, this nanostructured metal oxides or other nanostructured materials are quite sustainable in nature. Now, if we just build some sort of catalyst which can convert this water into oxygen, and simultaneously if it convert water into hydrogen, then we can get two important molecules, that is oxygen and hydrogen. And as I told in my first lecture, that hydrogen is now considered is one of the alternative of normal or naturally occurring fuel, because if you burn hydrogen in presence of oxygen, it can give you energy and you can run various things, and hydrogen driven fuel cells and many cars are now being developed. So, in this part I will be mostly focusing on the design of some inorganic material, and some part I will be talking some organic material also, which can catalyze this important reaction water to oxygen or water to hydrogen. Now, this schematic things I have already discussed, that if I talk about a catalyst, what should be the criteria, and if it is changing, you can call it pre-catalyst, if it is staying, it is a robust catalyst. So, I will skip this slide, I will come to here. Now, once we are looking water to oxygen or water to hydrogen, these are not simple elementary reactions, it has multiple steps. Now, typically in the left hand side, let us just take this middle part first, that what is water electrochemical water splitting. As I said, that if you take water and if you simultaneously oxidize it into oxygen and reduce into hydrogen by using two metal plate under a normal electrochemical condition, then we can split water into two components. Now, this, as I said, these reactions are not as simple as we think, because for the oxidation of water in an alkaline medium, it requires various multiple steps, because from water to oxygen you are basically forming a oxygen-oxygen bond, and that bond formation is very tedious, it is not as simple as we think. That is why we need a catalyst, and we need a potential or we need a external energy to build this oxygen-oxygen bond. And if you just start with, instead of water to hydroxide ion, because we are just taking out one of the proton from it. Now, first step of the water oxidation is the adsorption of the hydroxide molecule on the surface of the catalyst. Next step is, of course, the dissociation of the OH, that means the reaction B I am showing up here. It is dissociation of the OH to give you the O star AD, that means a oxo species that is on the surface of it. Now, third step is two oxo can couple together to give you a oxygen pre-oxygen molecule or O2 directly. There are some other possible pathways, because whenever we are having this kind of transformation, we must be having multiple possibility, and as I have taken that the star means that once the species is adsorbed on the surface. Now, in the first class or first lecture also I have discussed that the adsorption energy, how it is adsorbed, what is the dissociation energy, all these things matter once you do the electrocatalysis. How strong it is bound, how weakly it is bound, that actually controls the rate of the reaction, and it depends on the nature of the surface. So, if you can tune the surface property, then you can tune the rate of this OER, or commonly known as water oxygen evolution reaction, you can tune the rate. So, that means if you can cleverly design a catalyst, you can do the reaction in a very low or moderate potential, that means you do not need much energy to dissociate this water or hydroxide into oxygen. Now, if you took the other part of the reaction, because since this is oxidation, so it is of course happening in the anode. This is a classical concept of simple redox chemistry I am talking about, and if you just reduce water into hydrogen, that means it must be occurring at the cathode, because conventionally in a electrochemical cell we must be having one anode, one cathode. In anode it is having the oxidation, in cathode it is having the reduction. Now, I have discussed the oxidation reactions, that how multiple steps are involved there and how a catalyst can control the reaction. On the other side, this reduction part, water to hydrogen, is not that much complicated. It is pretty simple. It has only 3 steps, and these 3 steps are commonly represented by typical name Volmer step. That means how this water or maybe alkaline OH minus is getting adsorbed on the surface, and after the adsorption how H2 molecule is forming after another H2O is getting close to it and giving hydrogen. On the other hand, if there are 2 hydrogen adsorbed site combine each other, then also give you H2. Now depending on this rate of the reaction or depending on the mode of adsorption, it can be different pathway, and there are some ways in electrochemistry by which we can predict or we can say that which steps are actually occurring. So Volmer step is common for all the catalysts, but this Heroski or Tafel steps are different, and it also again depend on the adsorption energy, energy of the surface, what are the number of active sites, all these things actually matter. So that's why its battery is running low. Do you have plug point? Its battery is running low, this laptop. Maybe कनेक्ट कर दो इसको, नहीं तो टर्न ऑफ हो जाएगा. उसे ऐसे भी चेंज कर दो. I think it's coming. All right. So now these things is clear that if we want to control the rate of the reaction or yield of the reaction, then we have to control the surface of the catalyst. And again, I think better it's locked actually. Yeah, now it's coming. All right, so I have shown you already this strategy to how you can design a catalyst just looking at these 3 parameters. The same thing is also valid for water splitting, because as I said that you must take a catalyst in which the analyte adsorption should not be very strong, because if the analyte adsorption is very strong, it will poison the surface, or if the analyte adsorption is very weak, then the product formation will not occur. So that's why in this plot the catalyst must be having a optimum adsorption desorption energy, and we represent it as a volcano plot, and it is valid for both the reaction OER and HER. And it has been observed that most of the noble metals, platinum, ruthenium and iridium, they are having optimum binding capacity of these 2 analyte, hydroxide and water. So that's why they are very classical examples of noble metal which are used in acidic condition as well as alkaline condition to convert water into oxygen and hydrogen. Now as I already told you also in previous lecture that these metals are all the best so far, but there are inherent problem is that they are not very abundant. So that's why in laboratories in across the globe people are trying to find out some earth abundant metal based catalyst, so that we can have a optimum condition where the cost of the catalyst is also not very high,
but the activity would be very efficient. So with this aim, I have shown you again that we are designing multiple earth abundant based catalysts by taking permutation combination of these transition metals, where we are particularly focusing on this part of the material that is commonly known as wolframite type. Wolframite is actually a earth abundant minerals where tungsten is present with 3D metal. Now why wolframite? First thing is that wolframites are naturally abundant, and here molybdenum and tungsten, they are present in high valent oxidation state, and if you just combine them with the 3D metal, they are having a possibility to have a tight ion pairing. And these materials, this kind of wolframite structure having two metal site. Okay. So if you have two metal site, so you can have a option to switch from one side to another side to tune the activity and tune the property of the material. So that's why we have taken. On the other hand, it has been reported that wolframites are having some semiconducting in nature, and if you make this wolframite in nanostructure domain, then the semiconducting property can be very high. Now once you have a catalyst on electrode surface, if it is semiconducting in nature, then electron conduction will be very fast. Now if you have a very fast electron conduction, the rate of electrochemical reaction will also enhance. So that is the basic idea. Now we have also designed other catalysts, but I am not talking about those. I am mostly focusing on this part of my talk only on the wolframites and some analogous structure. Now here are some representative publications that are not relevant because it is not a scientific talk, it is a kind of a tutorial course. So here these two material I have taken, one is wolframite and its analogous structure, that is called spinel. I know most of the MSc student, they know what is spinel. It is also a naturally occurring mineral with a specific structure. I will be giving those structure once I will be going there. But first I will take the wolframite structure. The making of wolframite is very simple. If you have a just simple knowledge of MSc practical, you can do it in the lab. So where you can take a divalent 3D metal ion and take the corresponding wolframite precursor, that is MXO4. MXO4 is nothing but metal tungstate, sodium tungstate or sodium molybdate you can take, mix it with 1:1 ratio and do some hydrothermal reactions. Hydrothermal reactions are a special class of reactions where typically nanoparticles or nanomorphology are being adapted, or you can grow it. Now if you just simply vary this metal and this X, you can make a series of wolframite type structure. Now advantage here is that in this structure, although I have in the first structure I have drawn it in a different way, but they are isostructural. Isostructural means their lattice structure are very similar. They are all monoclinic packing. If you have some solid state chemistry in your MSc, then you know what is monoclinic structure. And interesting thing is that these color codes are given here, and in this color code you can say that each metal are having in each layer. Okay, so this iron is in one layer, tungsten is in one layer. So layer by layer arrangement is there. Now although their inner packing or atomic arrangements are very comparable, but due to some irregularity in the bond angle and bond distance that I will show you very soon, and some other parameters, they have different morphology. Morphology means how they are appearing under electronic microscope. So these are some transmission electron microscope. So Professor Raj also has shown you couple of images. So in these images you can clearly distinguish them, that although they are having a very structural similar arrangement of atoms, their morphologies are different. Now once you have different morphology, that means their energies are different. Okay, so that is, you need to think about it. Now let us take one by one and we will put on the electrode surface and we will do the analysis and how they are behaving under electrochemical condition, we will be seeing them. Now, as I said, once we are putting on the electrode surface, we are putting the bulk material. But interesting thing is that if you look into the repeating unit, in the repeating unit you will be seeing that one of the divalent cation and one of the XO6 are connected with one bridging atom. So, this is the junction. Now, if you just twist it little bit, you can change the direction. Now, if you change the direction, the atomic packing will affect. Now, if atomic packing will affect, then their bulk morphology can also affect. So, this is one possible way of interpreting that why we got different surface morphology, because here M is nickel and iron, they have different ionic radii, and since they have different ionic radii, these bond angles are different, bond lengths are different. So, if you just change atomically, if you change or tune, you can change the surface morphology also. So, that is the beauty of chemistry. Now, what else you can do? The else thing is that you can also vary their electronic state, because you are taking 3D metal. So, if you change the 3D metal, let us say from manganese to nickel to copper, you can change the number of electrons present in the valence shell. Now, if you change the valence shell electron, you can tune their activity. So, that is the idea behind designing this catalyst. Now, I will not show you much detailed result because it will be very boring for you, but I will give you the final result or conclusion. So, final result is that, as I said, that they have a repeating unit almost similar in all of the structures. So, once I have taken or we have taken nickel molybdate and nickel tungstate, formula wise they have very similarity, atomic packing wise also they have very similarity. Now, once we kept them under the electrochemical condition, and once we do the electrochemical water oxidation, we take 1 molar KOH as the electrolyte, and we find it out that once we have in this X we have MO, the structure actually breaks down very easily. If you do not put any potential, it degrades. Alright, in the first slide I have shown you this red cube which can convert into partial oxidation, complete oxidation. So, here in this example the structure is breaking down completely. So, this NiMO4, that is why is a pre-catalyst. So, it is actually not the catalyst. Now, once we took the other analog like tungsten 1, we find it out that in 1 molar KOH the structure is quite stable. So, if you just change the MO to W, they are having a change in electronic structure and it actually affects the stability. Now, here are some detailed condition I have given. If you go up to 1.6 volt, which is very high potential, in there also this structure is quite stable. On the other hand, if you take this NiMO4, if you just dip them into the alkaline medium, you are slowly taking out this tungsten because they are very labile in nature, and you end up with nickel hydroxide. And now, if you put nickel hydroxide for the longer time due to water dissociation, it can easily convert into NiO, and under electrochemical condition it gives you NiOH. So, that means from this study we can see that this NiMO4 and NiWO4, although they are structurally analogous and isostoichiometric, they have a distinct reactivity pattern. Now, if we compare their activity, just these are some typical linear sweep voltammetry, but I will give you the result only because most of you are not very familiar with electrochemistry. So, result wise it is saying that this NiMO4 derived NOH is giving you very high activity towards water to oxygen, whereas NiWO4 is not that much active. Now, this right hand side figure is giving us the idea that if I take NiMO4 and NiWO4, the surface area of NiMO4 is quite higher in compared to NiWO4. So, that is possibly one of the reason why these two analogous nanomaterial with different surface morphology give him different activity. Now we will then move towards another analogous structure, but we have now changed nickel to iron. Now if you remember, the nickel has a 3d 8 electron configuration, we are changing it to iron, that means 3d 6. Now let us see how they are behaving. Now if you again look back here, the repeating unit, so what we are changing here, if we have taken iron molybdenate and iron tungstate, so iron is same, we are just changing molybdenum and tungsten. Now if you have a basic idea about periodic table, the tungsten comes below molybdenum and it is in +6 oxidation state, so it is a basically 5d0 and 4d0 element. Now if you just look about their electropositivity, so according to the structure, tungstate or ionic radii, tungstate is more electropositive, molybdenum is less electropositive. So in this bond XOM, we are just changing the electronic state of the X and we are just changing the polarity of the bond. So once we are changing the polarity of the bond, that means we are changing from ionic character to covalent character. So most tungsten is the most electropositive, so that means the bond is ionic in nature. Now if you have taken already thermochemistry or some Born-Haber cycle, lattice stability, these are basic things that you have learned in BSc. So more ionic lattice is thermally and chemically more stable under common condition. Now here is also what we did, we just took iron and molybdenum, iron and X or M. Once we have taken molybdenum, we can see this is the delta HF. Delta HF is the formation enthalpy that dictates that whether lattice is stable or unstable. Here this computed value is 0.1 electron volt. On the other side it is 0.67 electron volt with a negative sign. Negative sign symbolizes that the formation enthalpy, because it is a negative value, and more the negative or mod value, the better will be the lattice stability. So from this we can understood that the once you have tungsten in the X side or the M side, the lattice is becoming very stable, and if a lattice is very stable, then it is, of course, it is very difficult to break. So same thing we can conclude from here also. If you just look into the dissociation enthalpy, it is 1.10, whereas it is 0.41. So apart from this nanostructure domain, if you look into their electronics and thermochemistry, you can find it out that dissociation of this material is quite difficult, whereas this is very easy, and that is the reason once we took NiMO4 and FeMO4, it easily breaks down into corresponding FeOH and NiOH. And since we have compared their activity, we find it out that hydroxide or oxyhydroxide species, since it is generated, it gives you the better electrochemical water oxidation. Now another series we have in this 3D series, we have taken a beautiful MnMO4 nanorod. Okay. So in this MnMO4 nanorod, this is the internal atomic arrangement. It is also a similar kind of Wolframite type lattice. And what we have found, if you take similarly as we have predicted that iron molybdates are generally fragile or they are unstable in alkaline condition, similar observation also we have found. And in fact, if you microscopically modulate them, you can actually track their changes. So here you can see that this nanorod in 1 molar KOH, if you dip it, this surface is getting chipped, or it is something is happening on the surface, and the surface is quite rough now. And this happens within few hours. And once we have characterized this chipped rod, we find it out that the internal structure has completely broken down into alpha form of the MnO2. Now here is not the end of the story. Now because our main aim is to use them as the water oxidation catalyst. So once we kept these nanorods beautifully aligned on the electrode surface and we applied some potential under alkaline condition, we find it out that it first transformed to alpha MnO2, then within the Sevi cycle it gives you slowly transformation of the delta phase, alpha delta mixture, and then in a long term condition it completely convert into delta phase, and that can be tracked through microscopy as well as we have already, the in situ Raman is one of the probe where you can directly monitor the electrode how it is transforming. Here you can see that this is the bottom black part with this 1 minute KOH. These are the Raman vibrations for the molybdate, MO double bond O and MOM, the terminal vibrations. These are the strong characteristic signal. Now once it was slowly exposed into KOH, there is a formation of new bands within 6 minutes of exposure on the electrode surface. And once we trace them with the progress of time, we find it out that there are some growth of new bands, and these new bands or this growth of these bands clearly can be correlated to the structure of alpha MnO2 and delta MnO2. That means on the electrode surface this MnMO4 is evolving to a new structure, that is alpha delta MnO2, and this is actually the active form of the catalyst. And now another thing also we can do, because we have a MOO4 and MOO4 give you very nice charge transfer. Now we can monitor also electrolyte, that how it is coming out. So that monitoring gives a rate of the leaching. So rate of leaching also we can fit it out in a pseudo faster reaction condition, and we can find it out this MnMO4 nanorod giving MO4 release with a rate, observed rate of 4.5 second inverse. That means in 1 second, apparently 4.5 is the rate of MO4 leaching. Now once we have deposited this material on the electrode surface, our primary aim was to oxidize water, utilize this catalyst, this nanorod. We find it out again that this change of the electrochemical redox feature in this region is also contemporary to this surface morphological change, because we are continuously losing MO4, and that's why you have a fluctuation in the redox feature. And also this current, this is called anodic current, is increasing pretty high, and that gives you idea that this is the pre-catalyst and it is actively generating MnO2 as the active phase to give you the water oxidation to oxygen. Now on the other hand, this is what I have told you, nickel MO4, nickel tungstate, iron MO4, iron tungstate. Now if you take a series from manganese to nickel, keeping tungstate constant, so what we are changing? We are basically changing the electronic state of this metal here. Now once we are changing this metal, that means if it is a octahedrally coordinated, then we can just draw simple crystal field theory. This is some textbook knowledge you need. So if you have a crystal field theory, then T2 GEGs are like that, because it's octahedral and you have oxygens are coordinated, so that means it's a high spin compound. Now if you just calculate their CFSE value along with the number of electrons, you can end up that once you have manganese, the CFSE is close to, not close to, it's actually 0, because it's a D5 system. If you move towards nickel, then slowly your CFSE value is getting negative. That means moving from manganese to nickel, you are increasing the lattice stability again, because you are gaining, because negative CFSE means gaining of energy. So that means moving from manganese to nickel, your lattices are getting more stable. Although they have a different bulk morphology, but that is their atomic repeating unit. So now once we have deposited all these 4 material individually, this nanomaterial, they have different morphology, and kept them on the electrode surface and applied some positive potential because you are doing anodic oxidation, we find it out that this first one, that is the MnWO4, within a potential of 10 CV cycle or 1.53 volt, that means you have applied only 300 millivolt extra potential out of your water oxidation potential. Again it started making the MnO2. Now next is the iron. Iron, you need relatively higher potential, that is 1.56. Now if you move towards nickel, even after 1.68 volt at 12 hours, you cannot break this structure. So that is the theory and experimental correlation you can do it, because as we have seen that more CFAC is more stable. So here this experimentally also we can validate that at higher potential nickel tungstate is quite stable. So that's how we have correlated its activity, and we find it out some of the representative active species during the water oxidation. Now I will move to the another type of lattice, as I have told you that this is also a bimetallic oxides, and once we prepared them we got the nanostructure morphology, but we must understand the basic repeating unit because it is actually giving you a lot of idea about its activity. Now spinels are one special class of material or special class of minerals. They have two metal in two distinct sites. So what are those two distinct sites? You have tetrahedra, you have octahedra. Now depending on the arrangement, again you can classify them in normal spinel and inverse spinel. Here I have particularly taken inverse spinel because Fe3O4 is one of the important magnetically active material in which this iron is distributed over two space in a different site. One is the tetrahedra, one is the octahedra, and iron 3 again is present in the octahedral site. Now if we just look into one particular surface, because once you are growing a nanoparticle nanocrystal, that also has a similar kind of surface just like a normal crystal. So if we look into the surface, particularly 001 surface, because there are a lot of literature which says that the 001 surface having a very high surface energy and it is actually active for the water oxidation or any kind of catalytic conversion. So this is one side view where the balls are indicating different metal. Tetrahedral irons are of blue, dark blue are the octahedral iron, and since it is a spinel, so of course ferrite, so if iron would be the only side. And here are the ball and stick model that how particular surface is aligned. Now the complication in water oxidation is that there are, as I said, that there are multiple possible reaction pathway, and which particular pathway is actually active for your catalyst, that is the tricky things to identify. And so far many people have worked on spinel ferrite, but the mechanism is not yet well established. So that's why it is very crucial to understand that which particular site, because as I said that there are two different sites, there are plenty of surface, plenty of atomic arrangements are there. So which particular site or two different sites are jointly participating in the reaction, that is very crucial to understand. Now since Fe3O4 is well explored, so we thought let's just take an analogous structure of that is the SnFe2O4. That means we are replacing one of the iron site with tin. Although we are replacing with tin, but they are having a similar lattice structure, that is you can predict it from the powder XRD, which is a technique by which we analyze the solid state or nanostructured material, and we find it out it has a very similar reflections, that means they are very similar lattice arrangement. So there is no change if you replace iron with tin, although they are having a different ionic radii. Okay. Now once we have kept them in under the electron microscope, we found it out that they are having a dimension of 5 to 6 nanometer, although they are not, homogeneously distributed. They have some heterogeneity, but the average particle size is approximately 6 nanometer in size. And they are also having a similar kind of atomic arrangement, but this gray polyhedra is represented by the tin atom. We are replacing one of the iron from iron to tin. And here is the another microscopic image that see that how the elements are distributed on the electrode surface. And you can see here tin and iron is very well distributed and equally homogeneously distributed. That means the material is present there on the electrode surface. Now we have done two different experiments taking a similar electrode. One is the oxidation, another is the reduction. That means once we polarize the electrode towards positive potential, once we polarize the towards negative potential. Once we polarize towards positive potential, it gives you water to oxygen, and on the other hand, it gives you water to hydrogen. The interesting phenomenon is that this material can act as a bifunctional catalyst. Okay, bifunctional means it can simultaneously act as an oxidant, simultaneously act as a reductant. And these are some matrices, that means by which we can determine whether the catalyst is good, it is bad, it is better, it is best. So based on the literature, these values represented by eta at 10, that means the extra potential that you need from the thermodynamic potential. What is the thermodynamic potential of water oxidation? That is 1.23 volt. If you add 263 volt, then you can produce plenty of catalytic amount of oxygen here. So that these values indicates that one. On the other side, this is the value for the reduction. So that much of extra potential if you put, it can give you plenty of hydrogen or catalytic amount of hydrogen. And these are some turnover frequency has been given. So I am not going into all these details of these individual matrices. We have compared a lot of reported data, and we find it out that so far among all the ferrite materials, this SN Fe2O4 is showing the better performance or far better performance than the other one. And another part is that you can build a electrolyzer in it. Electrolyzer is a electrochemical cell where you can have two electrode, simultaneously you can oxidize water to oxygen and hydrogen. Here we have taken only single catalyst on both the electrode surface, and we can do the dual performance, and it was stable up to 22 hours, so which is quite high in compared to other report. So that's why we thought, let's just in an aim to commercialize this material, we filed a patent in 2022, and this catalyst we have tested after the catalysis, because as I said that once you have designed the catalyst, you have to check whether after catalysis the catalysis structure is still remain the same or it is changed. So we find it out based on our studies that catalyst structure after 22 hours of performance, it was remain same. So that's why this is a stable catalyst so far. Now the question still remain that how this catalyst is active or how it is reacting. So in order to do that, we wanted to explore the reaction mechanism on the surface, because now we have tin and iron. So what is the role of tin? Why tin Fe2O4 is giving better performance than Fe3O4? So these questions we need to answer. So that's why we did some detailed electrokinetics. I will not go into the details because these are specifically for electrocatalysis, where we have varied the temperature, varied the concentration of the electrolyte, and we find it out some thermodynamic and kinetic parameter which tells us that activation energy on SnFe2O4 is very less in compared to Fe3O4. On the other hand, the number of hydroxide molecules involved in per turnover cycle is 2. That means in a one catalytic cycle, 2 hydroxide is participating in the rate determining step. So these values are indicating that. Furthermore, we have done also leveling study. That means if we have replaced water with D2O, the rate of the reaction significantly drop. So that means the OH dissociation is actually your rate determining step. So if you just connect all these parameters into one thread, then you will end up with some idea about mechanism. But although as being an experimentalist, always it is not very easy to draw all the steps. We can predict only this step is rate determining, this step is slow, this step is that. So for that, I just asked one of my colleagues to do some computational analysis. So he took the 001 surface of the SnFe2O4 where tin and iron both are exposed. And once it is exposed, so let's say if you have an arrangement like this where this M is the tin side and iron side is nearby. Now in the first step, what will happen? Since we are doing alkaline water oxidation, so OH minus will come and bind one of the site. Now for the time being, we have considered iron is coordinating with hydroxide, and if this M is iron, that means if it is Fe3O4, then it has been observed that this is the rate determining step where this OH dissociation occurs. Now if you change this metal from iron to tin, now the next step, that is the OO bond formation, is now becoming the rate determining step, because we have experimentally observed that the M of OH is 2. So that is also suitable or fitting with our theoretical prediction. So that means that in this material, the reaction is occurring in this way, but if you change the tin atom, iron atom with tin, then this OH, this peroxide bond is getting stabilized in presence of tin, and that actually kicks the reaction towards more catalytic oxygen conversion. So that's why here we have a synergistic participation of two metal together to boost your reaction. So that we can prove it from here. So I just want to summarize this part very quickly. So I have shown you two different material and what are their features under different condition. Now I want to move to this portion, because this particular talk supposed to be given by my wife, who is a student of Professor Raz Jelinek, and I am giving the proxy on behalf of her. So she is actually trained by this expert of carbon nanomaterial, and she is also now in NIT Raipur working with carbon quantum dot. So often, as apart from personal discussion, we often discuss the science also. So since she is working on carbon nanomaterial, so I talked with her and I said, let's just have a formal collaboration apart from personal collaboration. So they give us some of the carbon quantum dot material, and Professor Jelinek will also give you very detailed idea about what are the carbon material, why they are so interesting. So I'll just give you very brief one slide introduction on that, why carbon materials are also very important. Because as you see that most of the metal containing electrodes, we use heavy metals and plenty of metals which are, once we use it, you are just discarding it into the normal water, and there in wastewater plenty of heavy metals are there. So it is very difficult to purify them. So that's why people are thinking of using this carbon based material for this energy conversion studies. Now in this particular left hand side diagram, what I am trying to give you the idea that this is a typical phase diagram. Okay, it's a part of thermodynamics or physical chemistry. So if you take carbon and if you just try to correlate that in which form it is stable at room temperature, then of course the answer would be graphite, right? Now if you move on towards high temperature and high pressure, you can synthetically prepare diamond, which is very highly conductive, and also you can go into the vapor phase or conductive phase. And I know some of you, if you have done some practical on electrochemistry, or if you are doing some research related to electrochemistry, or if you have used any electrode, you might be encountering this kind of stuffs. So these are nothing but glassy carbon electrode, right? So what is glassy carbon electrode? if I just ask myself also or you, so glassy carbon is one form of graphite. So there is a nice Nature paper in 1971, they have found it out that glassy carbon is also kind of a graphite structure, but which is not regular in nature, but they have a random combination of basal plane and the edge plane. Edge plane is nothing but, let's see if I took a graphite which is some hexagons repeating in a two dimension, that gives you a graphite sheet. Now if you stack few graphites in a random this kind of structure, then it gives you a glassy carbon. And due to this particular arrangement, this glassy carbon is very, very conductive, because as I said, if you are doing electrochemistry, electrocatalysis, you must require a very high electrical conductivity. That means the resistivity of the substance should be very less. And here the observed resistivity of this substance is in 45 micro ohm per meter. That means if you take 1 meter square of the graphitic rod or glassy carbon, it would give you 45 micro ohm. So that is why the glassy carbons are very attractive, but the problem is that glassy carbons or this kind of making of these glassy carbons is not so easy, because at room temperature it is not formed. So you need relatively high pressure and high temperature. That's why if you want to buy this kind of electrode from any commercial sources, you have to spend at least 12,000 Indian currency, okay, which is not that easy to get. Now the idea here is, and the slide is also made by one of his student who is sitting here also, Anurag. He is a student of GGU. So these are the various different kind of carbon nanomaterials reported in different literature. And what are those? Fullerenes, nano onions, tubes, graphene, and these things. Even I am not expert in this area. The idea here is that since they are working in carbon quantum dots, and carbon quantum dots have a graphitic core, so that indicates that they are also having a high electrical conductivity. Now if you can tune the surface of the carbon quantum dot, where the adsorption of the water molecule or adsorption of proton, if you can tune it, then you can accelerate the rate or you can accelerate the activity. So in this domain, so Professor Bhattacharya's group, they have made recently a carbon onion, and it has been characterized by multiple spectroscopy, and you can see this nice transmission electron microscope is representing that they have a carbon onion framework in the structure, and it is also crystalline from the powder XRD, and the corresponding SAD pattern is indicating they are crystalline in nature. But our idea is to play with the surface structure, because the graphitic core is conductive, but it cannot adsorb water molecule. So if you change the surface with some suitable functional group which can adsorb water molecule suitably, you can do the electrocatalysis. With this carbon onion ring, we have recently done some water reduction, and we find it out that if you vary the amount of proton source near the surface, you can do electrochemical reduction of water to hydrogen very efficiently. So this is one of the collaborating work which currently is under review now. Another interesting work that is the carbon quantum dot, where they have varied the ratio of surface functionality just by varying the precursor. So that is sulfanilamide, and this is a citric acid precursor. If you just vary the precursor, you can make graphitic core, and you can tune the number of sulfanilamide on the surface. So what is the idea here? If you just change the amount of sulfanilamide, because sulfanilamide has a good tendency to adsorb proton in compared to carboxylic acid. If you have simple carboxylic acid, it will only be protonated, but it will never participate in the redox reaction. But if you take sulfanilamide, which is having a sulfur group, it is in +6 oxidation state, you can reduce it, and then this oxygen molecule will participate in the redox chemistry. So that's why if we just intentionally varied the surface composition or surface sulfanilamide composition, and we find it out once you have a carbon quantum dot with high sulfanilamide content, it gives you more hydrogen production. So this is one of two recent work where we collaborated